So first of all, the field of BCI has evolved over the years. And very often when we talk about neuroengineering, you would think about this is really great feat of technology here. What this picture is showing, this is surgery happening here, right? Where the neurosurgeon is inserting a deep brain electrode, right, for deep brain stimulation. And this actually, the surgery is happening while the patient is awake. So not fully anesthetized. It's a bit scary to know you're awake or you're aware, you're fully aware of your surroundings, and the doctor is now operating you in this state. Yeah, this is possible. Actually, in fact, is even necessary to keep the patient awake during this procedure, because you want to place the electrode in the right location, and you want to actually probe mental function while you validate, right, whether you don't stick the electrode in the wrong place, right? Sure, this is really amazing technology for Parkinson's patients, remediating this major disorder, kinesia as well as tremor. And it's amazing to see how activating this deep brain stimulation engine, what basically does it bombards the brain with this 130 to 180 hertz square wave signal that in the midbrain, because in basal ganglia, that concept is able to actually alleviate the symptoms of the disease. And it's amazing to see how a patient, we turn it on, had this essential tremor, and then after turning it on, the patient is able to actually do things, be active. That's great, but of course, there's many side effects of this procedure. And so the point I want to bring here is that, sure, there's really great technology, feats of technology, but at the same time, we have to be aware that there are sizable side effects. In fact, there's plenty of side effects of deep brain stimulation. And this is, there could be effective strategies that are much less invasive and more effective, that actually engage the brain in an active fashion as opposed to as a passive object in which you're intruding. Right. So the main message I want to give here is that, and this that line of research percolates with much of the work being done here at INC and also at in NYCU. So the concept of unobtrusive, minimally invasive, ideally non-invasive, brain-computer interfaces that close the loop and really get at brain function in an active fashion for remediating disorders that otherwise would be impossible to resolve. We're dealing, after all, with a brain that is a mental engine. It's not just purely a bunch of a soup of neurons that we can pharmacologically activate. So the concept here that we're all share, and you'll hear more about it today, is that of we go from pharmaceuticals for acting on the brain, on the diseased brain, towards electroceuticals. You use electrical activity in an active fashion to really interrogate, but also then modulate brain activity in ways that are synergistic with the healthy brain function, whatever is left, and also then stimulate the brain to navigate its own trajectories towards solving its own problems, right, in a dynamic configuration. So here we have the adaptive brain. Right, so you have an adaptive brain, or brains are massively plastic. You have also adaptive control around it, right? So very different from a usual static scenario that I just showed for deep brain stimulation, where you just bombard the brain with this static 130 or 180 hertz signal. And then you have this loop closed with a lot of sensing and modulation modalities, right? So this is work that was here done several years ago now at INC. So that involved Scott Makeig, who will hear about, was also involved in that, as well as Chi-Ping, Tersinovsky, also Dave Peterson, who's also, I think, is around here, and others, right? So this was a really a highly collaborative study funded by National Science Foundation. And the goal here was really very lofty, and I think there's still ongoing work, right, where we really can close the loop between sensing this concept of mobile brain imaging, which Scott will tell us more about, right, which really had its roots here at INC, right? Mobile brain imaging, along with motion capture. Another lab we have down here. So I recommend if you have time left to have visits to the labs here, right? And so there's different modalities for measuring brain states as well as body states, right? Then coupled with control functions, and then activating, in this case, have some feedback. What feedback do you want to apply for EEG? Well, what you typically hear about is visual feedback, and that's great, but you close your eyes when you sleep, for instance, right? There are many other modalities for direct feedback to our brain that involve sensory functions. So here we're talking about the that's a tactile function. You can also have hearing function. I'll get to the auditory modalities a bit later. And those are very powerful modalities, right? You can never turn off your touch. You can never turn off your audition. It's always there. And so those are great inroads into the brain that are very powerful, natural, unobtrusive, right, modalities for modulating brain activity, right? Okay, and then you close the loop, because then, of course, you can also figure out great models of how the brain works. That's with neuromorphic engineering. And once you close the loop, you can now really design strategies in which you can then really remediate lost function. The example here is the Parkinson's. Parkinson's is a disease that originates in the central, in the midbrain, basal ganglia. Now you can come up with strategies that can alleviate symptoms such as tremor or kinesia. Tremor, you can say, well, it's too simple to stop tremor. You just you put a brake on your arm, and of course, then stop the tremor. But that's not the point, because the tremor it's internal mechanism. It's a neurological disease. And so by getting at the origin of where the tremor originates, by the oscillations, the unhealthy oscillations in the brain, by targeting and basically using force feedback as a means for driving the brain towards attenuating the oscillations, but then through the plasticity of the brain over a longer time scale, decreasing that strength of this feedback to the point where the brain will naturally already circumvent those unhealthy loops. And so that's then a way of achieving on the longer term, through the long-term plasticity of the brain, short-term adaptation of the control functions, being able to achieve then a longer term, at least partial remediation of the disease. So that's the general setting, and that's what I would like to highlight now for the rest of my talk. Before that, so I mentioned brain models. Sure, there's so many complementary aspects of, as neuroengineers, figure out how the brain works with the goal of having interventions to solve major, I guess, neurological disorders. But complementary is the endeavor of neuroscientists. This is about analysis, right? And engineering synthesis, construction of bottom-up construction of control strategies goes hand in hand with the complementary analysis approach in neuroscience, right? Where you dive down to the lowest level of representation in the stack of spatial scales of how the brain works, rather than trying to solve it all at once, figuring out how the entire brain works. You bring it down to, you focus on say, either a synapse or even ion channels or whatever, right? So you go down to a detailed level of representation. And so if you join us at the Society for Neuroscience meeting, which typically every 3 years, next year again, will be held in San Diego, right? You have entire major a room full of posters, thousands of posters, where you have neuroscientists presenting every possible molecule or every possible neuropeptide or any all the molecular detail of what is happening. Clearly, systems neuroscience or neuroengineering allow us to put it back together, and so it's the two together that can allow us to make major inroads, right, in models how the brain works, and also at the same time having strategies that can be designed and for solving neurological disorders. So neuromorphic systems engineering is an endeavor that also here at UCSD and other places were really embracing to understand how the brain works and then actually build brains from the ground up. That can function as either really great models for AI, artificial intelligence, but also in the future for next generation of intelligent interfaces. What more intelligent interface can you have as one that speaks the same language as the brain, whether it's spikes, right? And so then you can use neuromorphic engineering not only as a tool for building more intelligent systems that explore the world, but also that can help bridge missing function that is there due to neurological disorders. And so here I'm focusing mostly on the other direction of this loop, right? So once we can build integrated circuits that can very precisely emulate what the brain is doing at extremely low power, being extremely efficient and resilient, we can use the same very efficient circuit design strategies for also building circuits that can now interface directly to biology. And so then you have circuits that both model what biology does and that can interface at scale to biology to then probe its function at scale, as well as also then modulate its function at scale. With learning and adaptation being key ingredients of that endeavor. But so now the main focus of today is not that this grand endeavor of building neuroprosthesis, right, at the scale at the nanoscale. But here today I'll focus on the workhouse here that we have at INC. Is mostly non-invasive, unobtrusive, EEG, and other sensing of brain activity, and closing the loop now for I guess neural prostheses that are truly unobtrusive, right? And so it just happens at all different levels of scale, you have also probes available that can match its function. I will not focus on molecular probes, although we do actually have molecular probes for, say, measuring metabolic function that we can couple even non-invasively, say, for in-ear sensing. I'll get to that in a minute. But mostly here we're focusing then on EEG, scalp EEG as a modality, right, for measuring brain function at the full brain level. There are other modalities in the middle, let's say for ECOG or electrocorticogram recording. You can also then have modalities where you can have electrode arrays, but then again, those tend to be invasive, although we can have some minimally invasive strategies there as well. So armed with those different modalities by which you can interface to our body, it's important for us to consider what can we accomplish with these modalities. And there, one metric is looking at what level of scale can we get at, right? And so here we have both spatial and temporal resolution that we have to consider. Ideally, we'd like to have our sensors and our actuators to cover the entire brain, right, at cellular resolution, all the way from milliseconds to lifetime, right? Clearly, it cannot be done, but so there's different modalities that each can cover at least part of this spectrum here, this temporal spatial spectrum. Each box here, the bottom of each box corresponds to the resolution, spatial resolution here on the left axis, and the top of each box corresponds then the spatial coverage, right? So ideally, the box would cover from top to bottom. And then again, so for temporal resolution, you'd like to go from left to right, from some milliseconds to 2 hours or even a lifetime, right? The important ones are the colored ones here that are unobtrusive and non-invasive, right? So forget about, well, MRI is not invasive, but it's definitely not obtrusive. You can find in this huge instrument. PET is definitely invasive. You inject all that positrons, right? But so the interesting ones are EEG. Now, ECOG and micro-ECOG, to some extent, they're invasive, but actually not entirely. There are some advances that we cannot make with micro-ECOG that actually be minimally invasive. Clearly, you want to stay away from penetrating micro electrodes, for those are definitely invasive. And if you then observe what it means in terms of accessing brain function, clearly, if you want to get cellular function, there's no way other than you have to stick electrodes in the brain, but that's clearly not for all of us, unless you're severely disabled and then there's little resort. You have to really, especially if you have to do surgery anyway, you might as well stick electrodes in that tissue. But then the less invasive modalities are then ECOG, sub or epidural ECOG, right? So electrocortical recording, just below or above the dura. And then the absolutely non-invasive unobtrusive one is an EEG that's on the scalp, right? But clearly, the farther you're away from the brain, the less resolution you have, because the skull in between will definitely act as a low-pass filter, spatial and temporal low-pass filter. And then you're only left with brainwave activity, is in the alpha, beta, gamma, lower gamma, not higher gamma range. And so that drove some interest to also going for ECOG, where you can, and actually, in fact, yeah, you can even get to micro ECOG technologies that are either modular or flexible, where you can insert through the fissures in the cranium, right? You can insert those tiny, I guess, chiplets, or those flexible foldable arrays, right? As opposed to the typical hard arrays that you have, or this large arrays that you have for ECOG. Micro ECOG means that you can resolve basically micrometer distances on the cortical surface. And so we developed what we call ENIAC, or encapsulated neural interfacing and acquisition chip. And now this shows how dated I am, and so others in the audience may still remember the old days of ENIAC as one of the first computers. This was a room full of vacuum tubes in Pennsylvania. In fact, researchers at UPenn, where ENIAC had its birthplace, recently, like 10 years ago, put all of the functionality with all the vacuum, so taking all the circuit that ENIAC was implementing for implementing that computer, put it all on a millimeter-sized chip designed by students. So today, you see how things have advanced, right, over the years with scaling, Moore's law. And so this is, of course, a pun on the name. We envision this ENIAC to be a first step in this revolution, where eventually we can have, there's a first demonstration where in the future we can have truly unobtrusive and non-invasive ECOG interfaces that are so tiny that you won't even notice that it is put on your brain surface. Here, this is still obtrusive. It's still 3 by 3 millimeters. Thickness is 250 micrometers. The chip is fully encapsulated, totally surrounded by insulator, which means there's no ohmic contact from the electrodes to tissue. It's all just purely so rather than getting Faradaic currents, this is purely capacitive coupling. And so this is one theme of our work is you don't need to have a wet contact to tissue in order to be able to measure bipotentials. You can rely on capacitive coupling, or at least dry contact, and you get still reliable recording of your bipotentials. In this case, 16 electrodes, and so we have additional coils around it for wireless telemetry. Think of this in your electric vehicle, right? So that you can actually send power wirelessly and power this chip from externally, just through inductive telemetry. Even more so, that coil also allows us to recycle energy. So you have this coil at resonance with capacitance that you have on the chip. And so the same principle of adiabatic energy recovery that you have in your electric car, right? When you push your gas pedal, sure, then you move energy from your battery to the kinetic energy of the wheels, right? But then later when you hit the brake, that energy goes, rather than just wasting it by a natural, just dissipating the energy by a real brake, you actually recycle the energy and bring it back into the battery. That's all possible with this inductive telemetry. Same principle. In fact, Tesla, the reason why Tesla cars are called Tesla, because Tesla came up with this inductive telemetry principle more than 150 years ago. In any case, so this chip now allows them to this fully encapsulated neural interface for both recording and stimulation. In this case, with stimulation, we can build up a voltage that is higher than the voltage you can actually acquire on the chip, and the way back, right? So when we stimulate, right, we bring the voltage up and bring it back down because you want to recover the charge after you deliver it. And it actually gets all the charge back and even more, all the energy back into the battery. So that's the concept. This was a paper that we had in Proceedings of IEEE. But now the focus of what I want to talk about here is then EEG. And of course, this is not a tutorial, but so where do these EEG signals come from? You have all those dipoles, and Scott will tell us a lot more about where dipoles come from, and so how we can actually have really good models of dipoles in EEG, and take advantage of them to separate sources of activity in the brain. But so yeah, this concept of you have dipoles everywhere, and you can then really measure them. Right. In fact, just the dipoles are everywhere. It's basically you get it's the effect of two monopoles opposing not charges, in this case opposing current sources, current source and current sink of equal magnitude that is separated at a distance give rise to this dipole activity. In this case, it's conductance. It is not electrostatic. And so, but you get the same kind of physics that plays out where those dipoles can be measured then anywhere all the way up to the surface of the brain, of your skin. And that's why we can measure brain signals on the scalp and heart signals on the chest, right? Just due to volume conduction. So preaching to the choir here because everyone here knows about this, but this is important to recognize this, right? And you have this really great, powerful techniques developed here at the Schwartz Center, right, of doing then this blind source separation. In fact, this has been championed here. So Chip-Ping is not giving a talk, but he is really Chip-Ping and Scott and Terry really started the field of EEG BCIs, right, by being able to doing the signal processing that's required for getting rid of all the artifacts. In fact, artifacts are signals too, and you can just separate them just as you separate them. So just as you separate the all the signals of interest, right? And then you can get this typical dipoles that can give you really important information. In any case, Scott will tell more about, way more about this, so I'll just stop there. But the important point I want to make, though, for purposes of thinking about in-ear technology, right, is that this dipole also plays out from the perspective of a pair of electrodes. When you have a pair of electrodes, right, a monopole, right, will give you the same kind of dipolar function of what you measure as a difference between voltage between two electrodes as a function of distance. In fact, it's also proportional distance squared. And you also get this angular dependence, right, same as a dipole. In fact, clearly, right, so the voltage that you measure is proportional to the distance between electrodes. So as you bring electrodes closer together, as you must when you say place electrodes on the surface of a hearing aid in the ear, the distance gets shorter, which means the potential, the field is the same, right? You measure whatever you measure field. So as you place electrodes closer together, the voltage you measure, of course, voltage is basically field, right? It gets integrated in space. So the shorter the distance, right, the less voltage that you have. Also, so that brings the signal down. The signal will be reduced. The noise also goes up because electrode size, electrodes, as they shrink, the resistance also increases. The contact resistance increases, which means there's more noise, right, contributed by thermal noise, right? And so you get an SNR challenge, right? The signal to noise ratio goes double down because the signal goes down and the noise goes up. And so typically what we measure when you place electrodes in the ear, typically there the SNR, the signal to noise ratio, decreases from scalp measurements by about 15 to 20 dB. And that may seem like, forget it, right? So it's useless. But what does it mean? If your SNR goes down by, say, 20 dB, right? How much more time do you need to collect data in order to get the same? Right? So it basically means that now what normally would take you a few seconds for detecting a certain brain state now will require you a minute or so, right, to detect the brain state. Right? It's just a matter of bandwidth of your recording. And that's perfectly fine if you're using this in-ear device for measuring sleep states, because if you're doing sleep staging, brain states, I mean, don't change on a time scale over time, just 10 seconds. Actually, how much time do you have left? Was it time scale? I didn't look at my clock. 20 minutes. Okay, that feels good. Yes. Oh yes. So I'll make it short. Yes, but yeah. So that's the principle here, right? So that we want to be able to resolve. in fact, you can, the magic is that, yes, sticking electrodes in the ear, you can actually pick up brain signals, just the same as you get on the scalp. There's, of course, difference because you pick up different dipoles, right? But still, with ICA, in principle, you have enough electrodes in the ear. In principle, you can still decode not all brain activity, but at least activity that is relevant. Now, what is relevant in the ear? Well, in the ear, you definitely want to get an auditory function. It just so happens once you're in the ear, you're definitely closer to the brain. And in fact, you're closer to the auditory cortex. So auditory cortex is not too far away. And so that's something that you can pick up there conveniently. And so yes, signals that you pick up in the ear are different from signals you pick up in the skull. But if anything, maybe we're a little deeper in the brain. And I wouldn't claim that we can actually get signals, say, from hippocampus or midbrain, but at least we're a little closer. Okay, but the point I make here is that there's an SNR challenge. SNR challenge basically means we need to do very careful signal processing and sensing, right? And we have to design the electrodes and the interfaces that give us extreme noise energy efficiency. What is this term, noise? So you can always get really a low noise measurement if you throw a lot of power at it. In fact, those two are almost inverse proportional, right? If you want to lower your input preferred noise of an amplifier, right? The noise power, the input preferred noise power, right, of an amplifier is inversely proportional to the power that you actually burn in your amplifier. So there's a one over relationship, right? So then so you almost have this trade-off, right? There's this fundamental, and that fundamental trade-off is given by thermodynamics, right? It's about, in fact, it's all about KT. KT is Boltzmann constant. T is temperature. Q is the charge of electron, right? 25 millivolts at room temperature. And so this is both good news and bad news. There's a fundamental limit that unless you cool it down, we can, of course, cool down your EEG instrumentation at cryogenic temperatures because then we're basically freezing the brain. So that's fundamental. But at least you can design circuits that can get as close as possible to this thermodynamic limits because we know them. We can, right? And so we're able to, so that we have defined those different metrics of noise efficiency factors that's been defined, not us, but you have defined in literature. And so this is metric that the closer you're to one, the better you are. And you can't get beyond one. In fact, actually, strictly speaking, you can go, depending on whether you have a differential amplifier or single-ended amplifier. For differential amplifier, you can go below 1.4, whatever it is, right? And so we actually we demonstrated our circuit design by careful design of optimizing the circuits for minimizing noise contributed by the circuits. We're able to get down to noise efficiency factors of a factor of 2, right? So the lower, the better. 1 is ideal, right? And so that's bad and good. It basically means we can't get much better than that, but also means nobody else can get any better than that. So we have assurance that that's the best we can do. We have done all we can, right? We can maybe get another factor 1.5 or so lower noise, but that's all we can do, right? There's some other metrics that also are guided by fundamental limits. So there's a figure of merit for ADD conversion and there it's typically around a few femtojoules of energy for each level of a conversion, and that's like we have optimized our circuits with that metric, as well as a metric for range efficiency for wireless transmission. Right? And so here are some of the circuits that we developed. So those are circuits that are, again, very energy efficient, inspired by how the brain works. I didn't say much about neuromorphic engineering, but in neuromorphic engineering, you can build circuits that operate in a thermodynamic regime. It's called a subthreshold regime that is very similar to the regime in which cells operate, also subthreshold dynamics. You get much greater efficiency in how you get much more gain per unit current, right? In that regime of operation than you get in the usual operation, where when you just, for the same reason, when you hit the gas pedal, you know, of course, you're going to waste gas, right? And so there are certain regimes in which you can operate a circuit too that are much more efficient, and we're able to do that. And this is how we're able to get microvolts RMS input preferred noise. You can resolve microvolts of bipotentials at microwatts power. Of course, what bandwidth? This is in about 500 hertz. So 1 kilo samples per second, right? Samples. So 500 hertz bandwidth. And so 1 microrod per channel basically means now you can in a hearing aid, right? This will last for months, right? For each channel. And so that becomes very viable. So now, of course, you spend more energy just communicating the bits that you, in fact, and this energy includes the energy for actually acquire. So this is all the way from front end, from the electrode, where you actually measure the potential, to the digital backend, right? Where you get now bits that come out, right? So you get bits, in this case, 16-bit resolution of the outputs, 32 channels here. Actually, sorry, this is 12-bit resolution, sorry. But yes, enough in this case for resolving your bipotentials. Another circuit here. Here we have 1,024 electrodes. This was meant for applications of in vitro or organoid kind of sensing, where we actually interface electrodes with organoids or cultured media in vitro. But the same chip can be used also for ECOG, right? We can place it on the cortical surface. So the pitch between electrodes is 50 microns. And so we have 1,000 electrodes here that can record bipotentials as well as also currents. Right? You can choose current or voltage by configuring your circuit either as a voltage clamp, right? You clamp the voltage and you measure current, or you clamp the current, means you apply a current and you measure the voltage, right? And so either way, we can get microvolts sensitivity at several kilohertz bandwidth, or femto-m sensitivity at 10 hertz or so bandwidth for currents. Current measurements is good, say, for if you want to patch clamp a cell and measure its conductance, etc., right? But also is important for potentiometric measurement, amperometric measurements, say, of redox potentials for say cyclovoltammetry, right, for doing chemical sensing. And we also get great efficiency of sending data across. In fact, we're able to send data. Again, the principle that we have here of the Tesla's principle, right, of recycling energy here too, right? That we're able to receive resonant energy from the primary into your wearable sensor, say that you're wearing, say, on the skin. At resonance, you get really good efficiency of the transfer. But even further, we can send data over the same link. And normally this was not possible. I can go over the detail here, but normally you waste all the energy when you send data back scatter telemetry, because then you just short all the energy, right? You dissipate all the energy. Well, here we figure out a way of doing it adiabatically, by which we only short the tank when the voltage is 0 and when the current is maximum. And in the process, right, when the voltage is 0, you don't lose any energy, and you keep circulating that current for one entire cycle, right? At the end of the cycle, now you open the switch again, and everything continues as if nothing happened. But at the primary, you can detect that change in impedance, and this how you can kind of sneak in a bit. You can send a bit back without dissipating any energy, right? Asymptotically, of course, there's still some energy, but now we're down to picojoules of energy per bit as opposed to nanojoules per bit. So you can have much lower energy for transmitting data wirelessly. We call it Cook, and that was also published in this paper here. Okay, so then we can take all that technology and then have this interface with this wireless sensors, wearable sensors. They can measure body and brain activity, even non-contact. Non-contact basically means here that the electrode itself can be at a distance away from the skin. There can be hair in between on the scalp, or there can be clothing in between, right, on the chest, and yet can still pick up the potentials, because as long as you have a very high input impedance to the amplifiers, in this case, very low input capacitance in addition to very high resistance, input resistance, they can actually still have enough capacitive coupling to pick up the signal unattenuated into your amplifier, right? And we demonstrated we can actually get EEG signals. In fact, that was a start of Cauwenberghs. So Makeig developed non-contact devices in my lab here at INC, then started the company Cauwenberghs, which now is called CGX. And you have seen these headsets. I think many of you have actually used the headsets. And so those are now dry contact, they're non-contact, but they also operate on the same principle of wireless sensing. In fact, there's an old version of this cognionics headset, but in addition, so out of INC also came work by Tim Mullen, also here at INC in Scott's lab, and who developed this SIFT framework, and then this became now. So after graduating, he started what is now called Intian for developing EEG pipelines, all with the Python open source tools. And this way you can truly do brain imaging. So this was work here with so both Chipping and Scott and Tim Mullen, Mike Shi, etc., right, for demonstrating this concept of being able to do in real time online, because brain computer interfaces. Okay, so now I'll just wrap up. So now, what about this in-ear sensing? So it just so happens that in the ear you have this great modality, right? Of you can actually really measure brain signals. We all wear things in our ears anyway. We might as well add some functionality there and actually sense activity in addition to just purely have it as a auditory interface where we just play music, right? And so it just happens that in addition to EEG, there's also other signals, EOG, like electroencephalogram, eye blinks, of course, EMG, muscle activity, even ECG you can measure, right? Your cardiac rhythm you can also measure here. And then there are all those metabolic signals, right? EDA, electrodermal activity, which is still, you can pick it up by the impedance of the electrodes. Basically, sweat gland activity can be measured by change in impedance. And then actual sensor that can measure lactate, sodium, etc., right? So those are all modalities developed in addition to things like cerumen, the earwax is another modality that can also be measured. So those are all rich signals that are in the ear that correlate with our brain and body activity that we can pick up. So here are signals that we pick up simply by having a hard shell mold where you have electrodes placed on the surface. We can pick up the both the auditory, potential as well as steady state potentials. We can observe both of those quite clearly, right? So this is the response to clicks, and here's you have the response to particular modulated tones at different frequencies. And you can even pick up like a finger prick the change in electrodermal activity. And so we took this technology and actually put it in the ear. This was work that was reported in Nature Biomedical Engineering a year ago now, where we lined the surface of an ear pod with a flexible array of sensors. In this case, we have 8 bipotential electrodes and then 1 lactate sensor that we have put on that surface, and we're able to measure them, those 2 signals simultaneously. So you can do metabolic sensing, it's sweat, and measuring then lactate in sweat, while also then measuring your E star G, the bipotential signals. And E star G stands for not just EEG, but also EOG and other modalities, right? They're all there. I won't go over the detail of how we fabricated this. This is a collaboration here with this is Joe Wang's lab, as well as Cheng-Hu's lab, and then Patrick Mercier on some of the side of the low power electronics. So we put it all together with all the sensors, and here are the signals we can observe. So we observed from subjects different auditory evoked potentials, steady state response, but also EOG, even the eye blink activity you can pick up, right? So ipsilateral versus contralateral with some differences there, but we can reliably pick up also then the eye movement. And of course, during exercise, we can then pick up changes in alpha activity post-exercise, right? And actually, there are correlated brain activity changes in activity levels in alpha after exercise that we can observe just directly after exercise and then a moment later. And so that's basically where we stand. And there's so many exciting things we can do together here. And let's leave it there. I'm not sure we have any time left for questions, but that's probably it.
Hey. We have time for a couple of questions. Any questions? Yes.
So I'm curious about the in-ear device that is measured for different modality of signal. Does it require different separated reference sections?
Oh, very good question. So the question is whether that in-ear device requires words reference, right?
Yeah.
And so that's why you mentioned we had this both ipsilateral and contralateral referencing, right? So as you can expect, right? So if you reference one ear versus the other ear, then of course you can get a really reliable signal, and you can get both the EEG, both the X and Y, right, of the EEG signal. The blue here is basically where the reference is in the ear, right? Where the reference is. And so we have, so in fact, in fact, we did some study to figure out where's the best place for the reference, right? And this is, right, there's part of the concha that is also exposed. Right, you can kind of see it here, right? There's part of it that still extends outside, right? But most, yes, so we actually did studies where we purely did referencing locally, right, between electrodes here. And so that's the blue here that we have. So even then you can pick up some level of your EEG signal. And definitely also the same with the ASSR. You can definitely pick up, so reference in the ear, you can pick up the ASSR. You can get a greater SNR when you do the contralateral, right, referencing. And that's the kind of trick people always use with in-ear, right? You have to be careful, you have to read the fine print. But yeah, we definitely demonstrated here, including this ipsilateral referencing, so purely in the ear. That's where we get this reliable ASSR signals. And I should mention it, but where we're going here, we don't care too much about EOG, but we do care about ASSR and other modalities where we can really modulate, where we can measure brain responses to sound. And our plan is to activate, close the loop actively, right, and do some remediation, right, of brain disorders by playing with this link. And then there, as long as we have a signal, even low SNR, over long enough time windows, short enough, small enough bandwidth, you can still have enough of power for doing closing the loop and doing in this case closed loop neurofeedback. But yeah, that's where we're going. Right? Yeah, but definitely that's absolutely important. And so often, if you don't, in many papers in EEG, you have to read the fine print because many of them will have reference, say, behind the ear or elsewhere. Yeah. But here, yeah, we did it definitely. At least part of the experiments were done with the reference in the ear. Thanks.
That's one question I want to ask. Because early days, I actually published a paper trying to measure SCCP.
Yes.
Using in-ear EEG.
Yes.
And then we found out the signals almost cancel each out.
Oh, yes.
The local
Yes.
reference. Yeah.
You have to be careful where you place the electrodes. Yes. And there's not much space in the ear. So, right. And as I mentioned, a close distance between two electrodes will basically reduce your signal quite substantially.
Yeah, I will save my questions later.
Yes, thanks. Yes.
Later discussion.
Thanks again.
But
Yeah.
for those young researchers, I have been working on it. You won't believe how significant this in-ear EEG will push the boundaries of EEG research. Because every time I gave a presentation about real world applications of EEG and BCI, people ask me questions: who is going to put on the EEG cap and to do recording? For instance, one paper talking about using EEG as a security check for instance, open the door. But who is going to put EEG just for that purpose? Yeah, so this one is very significant. Thank you.
Thanks so much.
So let's go on. Yeah, let's you have to log in.
Yeah, yeah. Okay. Yes. Okay. Yeah. Good afternoon, everyone. Yeah, this is Li-Wei from National Yangming Jiao Tong University. I do appreciate for Professor T.P. Zhong, yeah, his kind introduction about myself and also my team. Yeah, so today we are glad to share our recent research achievement, especially focus on we develop a wearable EEG or brain-computer interface, especially focusing on smart healthcare application studies. Okay, yeah, so first of all, yeah, this is our lab introduction. Yeah, so I do appreciate Professor Gert, yeah, your introduction, because we are also working on the dry electrode EEG, and also this year we have a headset model, yeah, so we're wireless EEG device, and already apply this on several neurological disorders, as well like a stroke rehabilitation or ADHD for kids or sleep studies. Yeah, so later we will share with you. And also today here, this is an example. Yeah, we use a brain machine interface. Yeah, for neural rehabilitation. So in the beginning, yeah, so I think everybody knows that what is BCI right now. So it's according to the definition. Yeah, so BCI is can measure CNS, central nervous system, activities and convert them to replace and restore or supplement or improve, several interactions. So here is a flow chart. So like a machine learning technology, we can acquire EEG signal and then after data acquisition, doing feature extraction, translation, and then translate to different comments. Yeah. Okay, so the BCI categories depends on their categories. Yeah, right now it can be briefly divided into 3 different categories. So like one is active BCI, and the other is reactive BCI and the passive BCI. So you can see here, this has a definition here. So for instance, like if you want to use your brainwave to control a drum or light or any external devices, so that's a kind of active BCI. And passive BCI is kind of using cognitive assessment, to analyze your human cognitive models, and then you can do several potential applications. So reactive BCI is between active and passive, and will provide a interaction or via external stimulation, for control commands. So based on the sensing type, it can be divided into invasive and non-invasive types. Yeah, so here I want to quickly share with you the huge trends about the research, especially in neuroscience and the neuroengineering. So you can see in the past few years, so the research records is increasing exponentially, speed. And also in BCI publications, so you can see it's also increasing, it's by exponential speed, especially after 2010. Yeah, so I still remember when I'm doing my PhD study in from 2004 to 2007. There's a very last study working on BCI topics, but right now it's very hot topic right now. So last year in 2023, TP and me, we published a paper in IEEE Journal of Biomedical and Health Informatics. We observed that so many study using study EEG studies, okay, from fundamental or any cognition studies. So it always has lots of papers, talking about that. However, we can observe a trend that it seems like more studies or move to the real world environment and started to use wireless EEG or wearable EEG devices. So you can see the trends is almost increasing, more than over 15%, in these studies. Yeah, right now it's also increasing a lot. And also from the CAGR, the BCI market value, so we can see that in 2023, it's already estimated around 7.4 billion, and in 2023, and probably estimate to increase to 13.7 billion, yeah, from in 2029. Okay, it's almost an increase of around 10%, yeah, 10.8% increasing, yeah, from 2023 to 2029. So it shows that increasing popularity and the demand for BCI technology. So in that paper, we also survey that after the trends, so we survey, lots of in the world, lots of the EEG related companies, okay, especially for the portable EEG devices. So it can be divided into like a wet device or dry or semi-dry or both. Yeah, so more than 16 wireless EEG devices, yeah, from different companies. So like Gert just mentioned, Cauwenberghs is also one of the company here. Yeah, so Makeig, they also develop the device. So we use a pentagram chart, yeah, to show that number of channels, sample rate, resolution, and the cost. Yeah, for you can see this. Yeah, so it's a radar plot. Yeah, to show to compare different device, their specification. And further, we also list lots of examples. Yeah, so which study paper using what device. Yeah, so this. So then it can be applied to different applications. Yeah, to some examples. Yeah, here. So that will be a beginning instruction for the, like TP just mentioned, the young neuroscientist or engineer, if you want to study your research. So what kind of device that will be more suitable for your use? Yeah, so you can consider to, yeah, to use that. Okay, so I also want to quickly share with that 7 leading BCI company, yeah, in the world. Yeah, so the first one is Neuralink. You may know that. So Elon Musk, and also Wearable. They also have a ear set, like EEG set here on Neurable, and also integrate with the VR goggles. And also Emotive, yeah, some people know that. Okay, it's already applied to many studies. Yeah, so in our literature survey, yeah, so Emotive cover lots of portions of the study, yeah, in wireless EEG device. Okay, and also this is kernel. Yeah, they are using a functional near infrared, yeah, device. Yeah, so here just share with you the quickly intro, yeah, about Elon Musk. They are invasive surgery, okay, study and put a brain chip, yeah, on the cortex field. So right now, Neuralink already performed the human clinical trial from last year. Yeah, so you can see some, yeah, medical news, yeah, there. Okay, so this is their brain chip, yeah, invasive on the cortex, and also perform some clinical animal studies of their ASIC chips. Yeah. Okay, so the challenge and the opportunity in BCI. So we are thinking that, so what, like the new sensor technology or need signal processing, advanced signal processing tools, and what will be the sensible real world application of BCI. Yeah. So from my point of view, we think that the core technology in BCI, yeah, it must cover, yeah, 2 major parts. Yeah, one is wearable device, and the other is AI or machine learning algorithm. Yeah, so we can call it AI in BCI. Yeah, so in Taiwan, NYCU, we developed the new brand, the wireless EEG device, and it covered the dry electrode. So in 2021, we published announced a graphene-based dry EEG electrodes, so it can help compensate the contact impedance, compensate with the materials like AG and the CU. Okay, the materials, so that can decrease in the contact impedance. Yeah, so through the graphene materials. Okay, so we published in 2021 in Journal of Neuroengineering. So Jay will share with more details. Yeah, because he performed the biocompatible test, because if we want to apply this kind of sensor or device into the clinical trials, yeah, so in the beginning, we need to pass the biocompatible test. And also the device must pass the electrical safety testing. So here we just show you our device already passed this testing, yeah, right now. And also we manufacture and assembling this EEG device by our teams. Yeah, so more than 30 sets. So here this year we also bring 2 sets, yeah, in TP's lab in the SWAT center, and yeah, do some testing or perform some experiments. Yeah. So in NYCU, we want to let the student so has the feeling what is BCI. Yeah. So in our department, electrical engineering, so we have a course called a human-centered computational course. So in the beginning, we let all the major students, undergraduate students, they work on the BCI experiment. Yeah, so that they can use the headset to control the drone, yeah, through very different signals, and also people can adjust the parameters, yeah, via the program. So in the beginning, no one need to implement the software or the algorithm first, because we already provided, yeah, to the students. Yeah, they can do it, yeah, online. Yeah, in the final project, they need to finish the basic mission, some testing or some mission challenge, yeah, for them. So that this is the first one, they just control their brain to move the drone, yeah, moving forward. And the second mission is that they need to pass, yeah, this one and and moving down and pass this, yeah, through and the landing. Yeah, so they need to pass the several missions and finish their project. Yeah, so after we can collect the EEG signal, yeah, so then we need to do because we will perform the data collection in the real world environment. So one of the major challenge issues is that we need to remove the artifact of EEG signals. Yeah, so in 2022, we published a paper in IEEE Transaction on Neural Network and the Learning Systems. Yeah, we applied the adaptive ASR, artifact space subspace reconstruction model. So basically, yeah, we define it. We use anti-Hebbian neural network to online learning, yeah, the artifact subtype. And after that, yeah, we can remove the artifacts, yeah, by the adaptive ASR in the real time of recording, EEG recordings. And further, we apply, yeah, the algorithm, yeah, into 3 different BCI data sets, like motor imagery, EEG, and motor imagery, and SSVEP, and also, yeah, the drone control, yeah, experiment test. So here we can see that the ASR algorithm, yeah, after ICA, so we can see their eye activity and also muscle activity will be reduced, and the SNR will be increasing, yeah, a lot. Yeah. So here is showing the online adaptive artifact space reconstruction for cleaning EEG signal. So this is for, yeah, single model. So you can see the subject just using, yeah, in the calibration state. So right now he tried to collect the EOG signal, and then after calibration and the training for 20 seconds. Yeah, so after that you can see this is after artifact removal, and this is the raw data. So you can see that it's real time can remove those artifacts, yeah, via this online adaptive ASR model. Then after that, right now we are, if you are familiar with ASR, it has a parameter need to adjust. So default is 20, a cutoff range. So after that, so we want to work on the real world environment. So like walking and the running and the staging. However, different cutoff, it must be a parameter, it must be adjusted in the online models that. So right now we are testing on the real time. So you can see the blue line shows the clean EEG signal, and the red is the raw data. So you can see that like even like this, the jumping or high noise artifacts, so it can be removed. Yeah, but in this such a big movement, okay, so the EEG signal still fluctuated or not clean quite not quite clean, yeah, in the processing. Yeah. Okay, so later, yeah, so then we have some promotion, like TB mentioned. Yeah, we received a IEEE CIS Outstanding Chapter Award this year. That is the main reason is that in the past few years, yeah, we publish lots of announced activities. Okay, promote many activities. For instance, this is the activity in WCCI in 2022 in Italy. Yeah, so we also let the participant attendees, okay, to test our EEG device, and also with the interaction with the robot, mini robot. And also we have a summer school. Yeah, you can see lots of kids. Yeah, they are attending. Yeah, so we have more than 160 participants from 12 countries, and over 100 online, and yeah, over almost 60 participants on site. So you can see Dr. Corey Stevenson, yeah, who is also as the postdoctor in my lab in the past. He stayed in Taiwan for 3 years. Yeah, Corey is Gert, a PhD student after graduation, so he came to our lab. Yeah, okay. So, and also we have some winter camp for high school students. Yeah, so they are also doing the testing. Yeah, okay. And also in Taiwan Medical Expo. Yeah, so we also showing several technology application to that, to the participants. Okay, so next, I would like to focus on the AI BCI in clinical application studies. So the highlight part, so our major focus is on the ADHD or stroke rehabilitation and the sleep. Yeah, so Jay, he will share the sleep study application, because that is a part of his PhD studies. Okay, here is share with you some publications. Yeah, so we have some algorithm and the control systems and the clinical trials, in different type of journals. That in the past year, maybe 3 years. So the main idea is that starting from the paper published in Lancet Neurology in 2019. So you can see there's a young person that's almost 25 years old, and through the invasive EEG recording, that can use it to control upper limb and the lower limb exoskeleton. However, it's already trained for 2 years, 24 months, and also it's through the invasive EEG signal. However, until now, the patient only can send start and the stop signal to initiate the walking. So before performing the exoskeleton, it must be do multiple training. For instance, like to train the left and right move it, or up and down, and also rotation and moving to the wheelchair control. Yeah, so we think that probably non-invasive EEG can also doing well. Yeah, so we propose an architecture of the multimodality BCI control exoskeleton, because the stroke patient, they need to doing neural rehabilitation step by step. So in the beginning, unlike the traditional machine learning model, so we can develop an algorithm to control it. Yeah, so we in different stages, like a standing and the walking and the sitting stage. So we developed several different models to that the patient to control the exoskeleton. For instance, in the beginning, they can train their concentration level, that the exoskeleton standing, and then move to walking. So we develop a topological convolution neural network, so including the spatial information, such that we can detect the MRCP or movement-related cortical potential to control the exoskeleton. And also, after they perform the long time rehabilitation, maybe 30 minutes or 1 hour, so they want to rest, so they can close their eyes and then as the sitting stage. So before that, we already developed a global cortical network. So because you know that for the foot control, so the EEG, the brain area, that will be in the central sulcus, in the middle of the central sulcus. So if you just use one channel EEG, that will be CZ channel. However, you cannot use just one channel EEG signal to separate what the signal will be right or left foot signal. Okay, so we use connectivity to differentiate that. So here is the network model. Yeah, we published in IEEE in 2020. Yeah, so then you can see the demo here. So once the subject move their foot, okay, this is normal subject, so it can be correctly recognize, yeah, the command. And then we developed a for the working model and doing the online testing. Yeah, so the model, the accuracy can be reached around 86%. Yeah, in comparison to other like EEG-net or convolutional neural network control.
Oh, it's not recorded.
So we observe that what type of convolutional neural network, yeah, their signals. So we use the MRCP detection. Yeah, we observe the independent component and observe that the convolution map after projecting on the IC component or independent component map. So they are almost all focused on the, yeah, you can see in the motor cortex area, and especially located in the central middle. Yeah, that's the the right position. Yeah, for control the foot. Yeah. So you can see topo convolution. Their features are majorly extracting from the central area. Yeah, so here is a demonstration. You can see that. So this is the patient. So in the first beginning, they need to look at the video, the scenario, and try to engage that. So then exoskeleton can help them to stand it. And then next, yeah, try to move their foot, yeah, to control the exoskeleton. So then exoskeleton will help he or she, yeah, moving, yeah, to doing the neural rehabilitation. So you can see right now it's already success, yeah, to control it. Yeah, if we here show the green line, yeah, it means that. Okay, after that, perform the multiple times. So if she want to rest, okay, so just close their eyes and then just. So after the clinical testing, so you can see the patient. Yeah, so she just left, and we just talk to the patient. You just use your brainwave to control the exoskeleton. So, wow, so amazing. So it's just using my brain, or just yes, we just talk to him. So after that, she want to move to the trial on the wall. Yeah, then perform more than half hours to doing rehabilitation. So next you see the neural OT and the PT, they still need to have a laptop for the patients. So right now we develop an immersive AR, augmented reality based BCI control exoskeleton. So you can see all the scenarios, it can be projected into AR and also integrate with our device, and also processing working on the small board computer. So then no need to have the computer or external devices for the patient. Okay, so this is the study for BCI for neural rehabilitation. I think quickly share with you the ADHD study. Basically, the main motivation is that FDA already approved that the game-based digital therapeutic model to improve the attention function in children with ADHD. So such that we can doing, that the kids play video game, we can say that they are training their attention level right now. However, how to evaluate the performance enhancement or not. So here are some survey review studies, talking about the detection of ADHD. So that's for your references. So we asked the kids to perform the CPT continuous performance test. So not only just divided them as a normal or ADHD person, but also we can evaluate their different types, like symptoms, like inattentive or impulsivity or sustained attention or vigilance. These are the typical phenotype of ADHD kids. So in NYCU, we already collected more than 289. Okay, it's close to 300 participants, and in different hospitals and also through different EEG device. So we also bought the latest Quick 20N. So that is also developed by Cauwenberghs company. So that is already FDA cleared. Yeah, so this device is the first one in Taiwan we already use in the clinical hospitals for collecting data from for kids. Yeah, so then right now we are leveraging all the data together and try to find a standard to differentiate the EEG, the ADHD class assistive diagnosis. Yeah, so here share with you some models. Yeah, we already published. Yeah, we ever use long short-term memory network that can just using on 101 beta, 02 beta can differentiate the ADHD EEG signal and the normal control EEG signals. Yeah, and the accuracy is around 85%, just using one channel. But if you use 8 channels, so that can reach 90%. And this year we published a paper using connectivity model. Yeah, so we can differentiate that ADHD kids. So their attention model, their attention connectivity in the frontal area. So that will be more connection, have much more connection. But how the ADHD kids, that will lose much more connection. So this is based on the visual task, or we call the CPT, and this is based on the auditory task. Yeah, so that's for a kata task. Okay, so different tasks, so you can see the different connectivity models, links, between ADHD and the normal kids. Yeah, so they implement that. So all the device, so we have a scenario and want to implement that. So all the kids in the one day, so they just wear our EEG device and then collect all the data automatically transfer in the cloud and automatic diagnosis by the cloud system and send a report to the children or their family. Yeah, so we already implement that and collaborate with our Guangda Quanta company. Yeah, so we already implement that on it, and this is the clinical test. Yeah, so we already applied it on the kids, and then while they are playing the game, okay, so all the data will transmit on the cloud and the analysis and the transfer to the medical doctors, in the clinical. So you can see here, the kids are playing the game, and then, so and then we'll show the online real-time cognitive state, so like attention, fatigue, or stress level. So here you can see that. So these are the cognitive state, the monitoring, attention, stress, fatigue. So after that, medical doctor will receive a report. So in the past, they just use the behavior analysis, for the diagnosis. Okay, but right now they might have additional like EEG analysis report, for their diagnosis. Okay. Okay, so I think I've leave some time for Jay, to share with our sleep studies. So here also showed some references. And he want to share. You want to switch. Okay. What?
No, just maybe we share the screen.
I think we need to reshare it again.
Jay is a visiting student from Professor Liu Post group, and he stayed at SCCN for 1 year. Has been NEMAR. Okay.
Okay, so since we're a little bit behind the schedule, so I'll make it quick about the introduction. So why are we doing this study? If we look back to for the last 2 decades in the consumption of hypnotics, you can see that I'm showing the left is the stats from Taiwan because I can find a stats for the US. But as you can see that from 2014 to 2018, there's a steady increase in the use of hypnotics in Taiwan. And Another group of researchers, they have done the study from another angle is from the consumption of the or the sales data of the traditional hypnotics like BCD and C drugs. And as you can see, that also in some developing countries like in the US, Canada, Australia, the consumption drops a little bit. The consumption in the emerging economic bodies like in Brazil, South Africa, India, China, and some smaller countries like Japan, South Korea, Taiwan, they are increasing in the past 2 decades. And also it remains hypnotic use in Europe remains high throughout the years. So as you can see, there's a huge market in the treating of sleep disorder and sleep difficulties. And what can be said offered in this market? So there's two opportunities. One is a market for easily applicable sensors that can be integrated with a wearable EEG device for sleep monitoring and diagnosis. And then the second one, sorry, got the number wrong. The second is that software for automated sleep analysis and also a potential for sleep quality forecasting. And I shall explain this later in my slides. So on the sensor front, as Professor Cole has mentioned, this is a sensor architecture we proposed in 2021. So it basically is a silicon-based soft body with integrated metal chips. But as you can see that those metal chips will have gaps between the chip itself and the human scope. So what we do here is that we use a smaller, more refined graphene granules to fill in those gaps so that in the end result is that the electrode will have overall better conductance and it can be applied without applying additional pressure or conductive fluid. So it can be easily take on and take off. And as we have shown in our previous study, this study we proposed 2 different compositions of the electrodes. One has 1% of graphene, one has 2%. And as you can see that both electrodes were able to reach about 20 kilo ohms of impedance after wearing about 10 minutes, and they start with 30. So it's almost like you can put it on, put the electrodes on the device and then put on the device and you can use it immediately. And as you can see here, we try to compare its signal with the traditional white EEG signals. And you can see that the signal correlation is pretty much always above 90%. So it's very, the signal fidelity is very high. And the last figure was resting EEG, but we also use like I think EEG to see that if it can capture other signals like EMGs as well as the traditional white electrode. As you can see in the figure, that both the electrodes were able to, both composition were able to capture all the EEG and then EMG signals with very competence. So this is the sensors technique we are using to develop our wearable EEG system. And then on the software front, we are also developing a software analysis tool because it is not enough to just get a signal, get the data. You also need to be able to interpret those data. So what we do here is we use a knowledge-based EEG classification system to convert extra knowledge on sleep EEG and sleep stages to be able to make a light system to automatically classify sleep stages. And this system only requires 1 channel of EEG signal. And basically we use the EEG signal and decompose it using the Ph.D. analysis and also entropy analysis and use those as features to feed into the classifier. And what we have noticed with previous, because there have been many studies about automatically classify CEG using various architectures and deep learning network. And what we found in those studies that's lacking is that most of these studies were done on a single set of data sets. So this you only know that this method theoretically they works, but will they work across different devices? Will they work across different ecosystems? That is a question meant to be answered. So what I do here is to first we'll train the whole our algorithm on a 14 subject data set, and then we exclude those training data set, and then we use another data set that consists of 18 subjects and covers 3 different EEG classification systems to validate if our trained model can be used across different systems and be deployed into various environments. And as you can see here, indeed, while the model achieved about 80% accuracy in the original test data set, training data set, and it was also very competent in other classification in other EEG systems. And there are some rare cases like this one when the original Ph.D. signal was filtered with a more narrow bandpass filter, so it has some low frequency signal that's getting wiped. So the classification gets a little bit worse, but generally it works if the bandpass was set at the right range. And then that's for CEG. And then we have another idea is that because the first software is used as a after the fact analysis, like you went to sleep and you wake up and you put your EEG into a software system and you see a result to see if you sleep well or not. But what if we can predict sleep qualities with resting EEG and be able to help the subjects get a better sleep qualities? So the idea is that our mental state may be affecting the sleep quality. So I mean, as most people have experiences that if you're anxious or you're in high stress before sleep, you will usually have a harder time falling to sleep, and you will usually come out of sleep with a little bit tiresome. So we hypothesis that pre-sleep stress might be influencing the upcoming sleep structure. So what we do here is that we use 2 frontal EEG channel from F3 and F4 in the frontal lobe because those are highly connected to psychological stress, and then try to see their relationship with the upcoming sleep structure. And what we found is that in subjects lacking slow wave sleep or lacking deep sleep, they show a very high negative beta delta recent correlation in pre-sleep EEG. While those with a high amount of slow wave sleep, the orange one and the green one, they show a much smaller correlation in beta delta correlation. And beta delta correlation there have been studies suggesting that it's symbolized cross-link between cortical and subcortical brain region that is sometimes activated when a high social anxiety or social stress is imposed on the subject. So this is a sign that perhaps those experiencing less slow wave sleep or having higher anxiety and stress before they fall into sleep. And then we also examine other indicators like alpha asymmetry, which we use a formula to turn into a stress indicator in the bottom right. And as you can see that those have low SOAC tend to have higher stress than subjects. And we also check it with the entropy analysis and found that those who are experiencing less SOAC tend to have higher signal entropy, and also I'm not showing here, but we also found that they have higher spectral entropies in their preset EEG. And since we found those neural markers, we figured that we might be able to actually use those markers to build a predictive system to see if the subject is going to have a hard time following is going to have a poor sleep quality. So what I do here is we use this structure to fit into your traditional supervised machine learning system. We didn't do much thing fancy here. And we actually found that the classifier were able to identify EEG fragments from those who were having less sleep with up to 75% accuracy. And we, if we refine with a more advanced classifier, we can see we might be able to push the accuracy well over 80 or 90%. So from this, we may build a alert system that the scenario will be the subject before they fall asleep. They will do a short time EEG recording, like maybe 3 minutes and 5 minutes. And if the system detect that the subject is having stress and might have a difficulty falling asleep and bad sleep quality, you will be able to alert the user. And then in the easiest sense, it can help the user to relax with either sound or music or breathing inductions. So, and in a more advanced sense, the system can also be implemented in that if it's detecting the subject is going to have a poor sleep quality, it will be able to control the environment to help improve the subject's sleep quality during the sleep. So this is what we hypothesize why might be working in a BCI sense. In fact, we have a wearable device that's using the dry electrodes that we showed earlier, and you will connect through a mobile app. The app will upload the data to a cloud server, which will do all the processing and prediction and analysis. And then it goes two separate ways. One is that it can feed to the clinical personnel, so the doctors and the nurses will have a better understanding of the subject's usual sleep patterns. And also it can be feedback to help subjects either have an easier time relaxing, or it can use to control the environment to help improve the subject's quality. And here, since we're running out of time, let me just show this video real quick. So this is the device we're currently building right now, and it's connected to this app. And this map, before you fall asleep, you just put this on like this. And since you use the dry EEG electrodes, you don't need to prepare a conductive fluid or gel before you put this on. And then when you put it on, you just hit record and wait a minute. Right, let's just skip. And after you put it on, you just hit record and then you go to sleep. And when you wake up, you just click start recording and then you can see the results of the analysis and see how you sleep last night. And this is, we're still doing some initial testing of the system. Yeah, but this is where we're at now. We have the first half of the sleep BCI system completed, and we trying to finish up the second half, the bottom left. Yeah. So this is my presentation, and yeah.
Okay.
Mm.
So that's it. So it's
Any questions?
Thanks.
Very exciting. So now you can close the loop, right? You can improve the sleep based on your feedback.
Yeah, that's our the main idea is that we can use the neurofeedback to detect if the subject is having a problem with the sleep, and the system will automatically try to compensate or rescue that. So that's our end goal.
Yeah. The intervention could be anything from maybe meditations, stimulations, or just listen to music.
Not an alarm though.
Well,
Yeah.
I left out due to time issues, but we actually done a study that study the effect of lavender aroma on CEEG and sleep quality. Actually found that the aroma will help improve sleep quality and prolong slow sleep. So that is also a possible application. You can connect it to a aromatic oil dispenser, and you will release it when you fall asleep, and automatically improve your sleep quality.
yeah. So Jay just sorry, we need to reshare again. Yeah, Jay just mentioned.
Now to
Yeah.
better sleep.
Yeah. In this idea is that
Yeah, this is our study. So that is a single blinded. We use single blinded. So after the participant, just after first the sleep cycle, so we turn on the aroma stimulation. So the participant who didn't know, yeah, the aroma stimulation last night or not.
What aroma?
Lavender.
What
Lavender, very typical flavor. So, you know, after we published this paper in 2020, 2021, so there's a company called the Blue Seed. So they just visit our lab, and then so they want to know what's the flavor or what's the specific, materials we use lavender, the lavender we use. Yeah, but I say if that's a typical ones, I didn't have the detail because we don't want to promote the lavender. Oh, yeah.
I think Toyota was working on that.
Yeah. Lisa. Oh yeah.
Peppermint.
Yeah. Yeah. So yeah. So after that, around close to the 5th or 6th cycle, yeah, before the 6th cycle, sleep cycle, so we turn it off. So after participate, they wake up, we will ask, do you smell the lavender flavor last night? So they all answered no. Yeah, so it's a control we call the single blinded. Yeah, so we have additional night, yeah, for just using water, yeah, split it, so they know, okay, they were under the construction, yeah, the condition.
It might be used for other kinds of drugs.
Drugs, yeah. Well, yeah. Yeah.
Okay.
Okay.
I said he is I'm his frequent visitor because before COVID, he come every year.
Yeah, every summer.
Every
Yeah.
summer.
Yeah.
And this year he is going to be here 3 times. This is the first time he's coming back.
Yeah, because we got a grant from our NSTC, National Science and Technology Council. So it's called a Dragon Gate. It means that sponsor a team, PI and the students, to visit a lab. Yeah, so student must visit here for 1 year. a PI must stay here for at least 2 months. Yeah. So encourage all our Taiwanese students, yeah, in the future when you are studying, so you can apply the grant directly and also stay here for a long time. Yeah.
Okay, we will take a short break. Let's see. Now it's 13. So let's come back at 8:30.
Right?
Yes, Corey's online.
Oh, really?
Hey, Corey.
Hello.
Yes.
Hi. How are you?
I'm good.
Yeah, I
We're
suppose
talking about you.
yeah. I also share with our photo while you are in Taiwan. We organized several activities like a summer camp, yeah, and some conference workshop. Do you remember that?
I very much do.
Where are you now, Corey?
San Diego.
Oh, San Diego.
Yeah,
You
yeah,
mean a
very-
few miles from here then?
Yes, this is a general session though, so we can talk about this another time.
Of course, of course.
Cool.
Yep. We also have Masoud that joined all the way from Lebanon here too.
Oh, really?
Yeah.
Um,
People from Malap are joining
Hi,
in.
Gert.
Hey Masoud, how are
Great
you?
talk. Thank you guys for making it online. Good, good.
Is doing nanotechnology,
Oh,
develop also different electro
okay.
technologies at
yes, yes, yes.
yeah, tell us about Masoud, because your students have been developing some really great low impedance electrodes too, right?
Yeah, yeah. We presented some cool work in EEG-Based. Mainly, we're perfecting inkjet printing to build devices on very flexible material. Inkjet printing is pretty cold. It's cold processing, so we can use very flexible devices that degrade and gives us a chance to build quickly, build small. We've been building amplifiers as well. We just had a paper in ACS interfaces that got accepted. Ph.D.'s work.
That's right.
Very
Yeah.
nice work.
Yeah, just a few devices for implementing a gain element, right? Yeah.
Yeah, yeah. Hopefully we'll scale. The goal is to scale up.
Mm.
Thinking maybe 50 to 100 to 100 sites. Basically a transistor for each site. So should be cool going forward.
Yep. Great. So we have here the
Yeah, by the way, I bring a
Oh.
tea from Taiwan.
Oh,
because
thank
right
you.
now, yeah, because I give you a name card. New
Oh,
name
thank you.
card.
Yes, yeah. Yes.
Yeah, then
Oops,
you have to
turn off my
turn off
sound.
the sound, yeah, speaker. Yes,
Yeah.
yeah, good. I'm
Nope.
going to introduce
No,
you.
no, it didn't. There's still,
Oh, because there's another one.
oh, yeah.
Okay. Oh, clean.
Mhm.
Oh,
Oh, there you go.
bigger than life.
All right.
I will introduce you.
Okay, good.
You want a long one or short one?
Oh, short one. Turn up volume. No, I don't want to do that. Okay. But now I want to, oh, so now I want to share the screen.
Yes.
I will, let me do that.
Cool.
And now here we are.
People stay up the whole night in Taiwan listening to
Oh,
talks.
oh,
Because it's 16.
okay.
Oh, Cheng-Shu actually is listening too. Shang.
Uh-huh.
He said he might come back from next week. I don't know if you will be.
No, I'm going up to Schwartz meeting
Oh.
Monday, Tuesday, and then I'm staying in Seattle for,
It's good.
well, probably the last meeting. Yeah. I'm gonna see Terry tomorrow, though.
Oh.
Tomorrow here at 10. We'll see what he thinks. But we should have a talk before we go. Saturday would be also possible.
Yes. Okay, welcome back. So let's move on. Oh, what happened? Yeah. Okay, now it's my honor to introduce the next speaker, Dr. Scott Makeig, who is the director of our center, the Schwartz Center for Computational Neuroscience at UCSD. Scott and I have been working together for 31 years, 31 years, since 1993. Scott is a leading figure in cognitive neuroscience, renowned for his pioneering work in the analysis and modeling of human cognitive event-related brain dynamics, such as event-related spectrum perturbation. He invented in 1993, has actually influenced the field tremendously. Also, independent component analysis. As you know, he is the principal investigator of widely used EEG lab signal processing environment for MATLAB, which has revolutionized EEG research. According to Google Scholar, his work has been well received and cited by the field with over 76,000 total citations. His current research focuses on the NEMAR project, which he will share in his presentation, and mobile brain body imaging, or MoBI. MoBI integrates EEG with simultaneously recorded physiological data such as eye tracking and body motion capture to explore the dynamic relationship between brain activities, cognition, and behavior. So without further ado, let's welcome Dr. Scott Makeig.
Yes, thank you, Ziping. It's been my real pleasure to work with Ziping for 31 years. I never heard of 30 there before. I would always say 25, and he would say, no, 27. And then 27, 28. So now it's all the way to 31. And it's been a pleasure always to work with him and all his colleagues who visit us from Taiwan and other places. So Ziping asked to give a kind of a summary or survey of what we've been doing here at the Schwartz Center for Computational Neuroscience in the last 22 years or 23 years, and before that for some years at Salk Institute in the laboratory of Terry Sinofsky. So I'd like to begin with this little poem that I wrote, prose poem. I called it Embodied Agency. The brain supports our life as a human being, embodied in a body in the world. And so just uncovering how brain dynamics support our experience and our behavior is one of the most intriguing and difficult and exciting scientific projects. You know, there's so many billions and billions of dollars spent on space telescopes to try to see the structure of the universe and how it expanded or how it is expanding. But the intricacies of brain dynamics on multiple scales at once is no less exciting and fascinating. So I write here that brain processes have evolved and function to optimize the outcome of our behavior, which the brain organizes. So the purpose of the brain is to optimize the outcome of the behavior it organizes in response to perceived challenges and opportunities. But those opportunities come every moment. And those challenges come every moment. Brains meet the challenge of the moment, every moment. And because of the great complexity of our environment,
Let's make sure you're right. It's on.
Oh.
It's on? It's fine, it's good. It's good. Sorry.
Yeah, because of the complexity of our environment, the world we live in, that means brain processes have to be equally complex and also malleable. They can change from moment to moment depending on the challenges and opportunities, small and large, that we perceive that cause us to shift our attention, our intention, our focus, and that makes brain studies really a deeply fascinating scientific study, and it gives also engineering new vistas for creating systems of use to people. So there's a perpetual cycles in supported by the brain of evaluation of what's happening around us, to us, in us, of making appropriate behavioral responses, perceiving the results of those responses in the light of the evolving events and context in which we're living. So it's this difficulty which makes also the mathematics of analysis of brain activity difficult, but also fascinating. Okay, so the Swartz Center began with a gift from Jerry Swartz, an inventor of barcode technology using lasers. In 2001, he formally began the gift, and we moved into off-campus housing in 2002 across on the other side of the campus here. These were our offices, and I wrote that the goal of the Swartz Center for Computational Neuroscience should be to observe and model how functional activities in multiple brain areas interact dynamically to support human awareness, interaction, and creativity. I wanted to go far beyond just visual perception and the like, but to look at the higher order capabilities of the human brain to support our creative life, our social life, and not just look at simple perception or memory or the like. We moved here to this building when it was new in 2010, and these are the offices that we still have on the other side there. Plus, there were offices upstairs that Ziping has been using. And then, of course, I hope you all get to see the MoBI lab downstairs. So this was our 10th anniversary, I believe. It's covered over here, so I can't see. And at that time, there were almost 50 people associated with the Swartz Center, probably the largest laboratory for EEG studies at the time in the world, I would imagine. So many visitors we had from so many different places that really have always enriched the life in the laboratory. The one time when we got our surround sound system down in the MoBI lab, I asked people to record a story in their native language, in their home language. And then we mixed them into a babble as an experience, like a sound experience. And there are 12 languages in the lab. And that richness is really something I personally have enjoyed. So as Ziping said, our EEG lab software fit a need for open source, freely available, and open and readily extensible environment for EEG signal analysis. And so in 2011, there was an actual survey taken, and EEG lab was quoted as being used by more cognitive neurosciences than any other system. And if you look in the citation index, the citations into EEG lab are still leading in the world. So what is this EEG that we've been working on all these years? Well, this is a picture of Walter Freeman, who recently died in his late 90s, I think, in University of California, Berkeley, who was the one to look at small grids of electrodes placed on the surface of the cortex of animals, and where in his key observation was that sometimes the phase portrait of the activity underneath the grid changed from a disorganized pattern to a very organized pattern, and he likened it to pond ripples going in and out. And so this organization at macro, or he called it meso scale, of brain activity, he thought deserved much more study and must be much more important for function of the whole organism than was given any credit in the era of single electrode, single neuron based modeling. I think that's still true today. So what is when you record from the scalp, of course, you're recording the difference between two or more electrodes in potential. So I asked my colleague, now retired Zeynep Kellanachar, to make a map for a particular model head that we have from a MR image, make a map of where the electrical potentials arise in the cortex that produce this one signal from this one scalp channel. And in other words, what is the receptive field of a bipolar EEG scalp channel? And this is, there's Zeynep with her son now taller than she is now. And this is the answer. Anything on this is the map of the weighting of activity summing to this single channel. Any place on the scalp that's not bright green has some contribution to that single channel. Any place on the cortex that's not bright green. And the red and blue indicate opposite signs. So if you do the dot product of this map with the actual momentary activity in the whole cortex, you get this one value, which is the voltage at that time in this single channel. So,
So this is not unique, right? There are different fields giving rise to the same potential to measure.
well, no, from moment to moment. No, this is given by, this is a static projection, right? It depends on the conductivity and the geometry and the conductivity structure of the tissues. It's linear projection, and it's constant within, unless you get a bash in the head or something. But so at every moment, the signal that you record in that channel can be from a different combination of places in the head, weighted by this same map. So there may be negative potentials in the back of the head that, of course, negative times negative will produce positive potential in the scalp channel. Or there may be positive potentials in the front of the head that may produce a positive potential in the scalp channel. And both of them may to various extents, and then negative and positive potentials. So that is to say, EEG is really very fuzzy spatially. It's not scalp imaging is not brain imaging. That's the fundamental problem with EEG. But the projection is linear, and there are no capacitive effects below about 1 megahertz according to electrical engineering. So that gives us a hope. But we should always remember that the raw signals recorded non-invasively on the scalp is not the same as brain imaging. And yet the only signals of interest are from the brain. We're not interested in what occurs in the scalp any more than when you study EMG, you're not interested in what happens in the skin cells. You're interested in what's happening in the muscles beneath the skin. And it's too easy in the general field of EEG studies, either in neurology or in psychology or wherever, to forget this basic fact. So this is the beauty of the ICA decomposition, which very fortunately I discovered when I was working with Ziping, and he was sitting in Terry Sinofsky's lab, and Tony Bell and Terry wrote a beautiful paper, and we took it from there. This is 15 seconds out of a half-hour recording, and some 9 channels out of 100 channels that we recorded. And so the decomposition was about the whole half hour. Here we only show 9 channels for brevity and only 15 seconds. And what you see is the smearing of, for instance, the large spiking eye potentials, eye movement potentials across the scalp. And the other emanations from the brain are smeared out across the scalp, as according to the map we saw. And here are 9 of the 100 independent components, processes, that ICA decomposed the joint signals into. And we see the meaning of independence here, temporal independence, that having information about at a given time t about any one of these signals gives us no information about the other signals. That's not quite true here for the eye components. I'll get to that. Here is a ECG artifact in the EEG, and here's its projection. It projects to all the scalp channels almost to a certain extent. Green here is always 0. So here's for instance, a spike, an ECG spike, and you can see it a little bit in the raw, some of the channels. You can't see it in the other channels. And yet ICA finds its spatial projection and and cleanly pulls it out from everything else in a way that no other filtering method could do. But these two components, signals, are obviously not quite independent, right? One occurs, the spikes in one of them occurred just before the others, and this represents a slow eye blink potential. The subject was blinking just before the new signal came in. This was a 2-back performance task. ICA separates out the eye activity from everything else. But it remains true that what ICA really does is separate the signal, the joint multi-channel signal, into independent subspaces. And here is a subspace of that's not quite independent of two, consisting of two dimensions that are not quite independent of each other, but it separates that subspace from all the other subspaces. And when the subspace is one-dimensional, then we can truly say that's an independent component. It contributes independent information to the EEG signal at the scalp. Here is alpha burst, bilateral alpha burst that was produced at the end of each trial for the few hundred seconds of rest before the next challenging stimulus appeared. And here is a close-up of some of that activity. You can see that the resolution produced by the signal-to-noise ratio produced by ICA is such that you can meaningfully look at single trial differences. Below it in red, I have the ERP just reproduced. If you take all these 1,000 trials that were in this experiment and you average them, you get an ERP, event-related potential, time to the onset of the visual stimulus that the subjects were responding to. And you see the ERP collapses all this rich information about what's going on in that particular brain structure that ICA identified as a major source of the signals. And then you lose all the temporal individuality and complexity of what the brain is doing if you just use, in this case, even this average across trials indiscriminately. So the beauty of this ICA method that we've worked on so long is that the components that it finds, are the effective brain components among the components that it decomposes high dimensional EEG into. The scalp maps, their projection patterns to the scalp, almost perfectly resemble an equivalent dipole, something like a theoretical tiny oriented battery whose projection to the scalp were it just placed there would be equivalent to the projection pattern or the scalp map associated with the actual independent component learned from the data. So this led to a paper in 2012 led by Arno and with important contributions by Jason Palmer, in which we compared around 20 approaches to ICA decomposition. And we found that the better an approach worked in terms of the more mutual information it wrung out of the channel data when converting from channels to sources, the reduction in mutual information between the channel signals and the independent or maximally independent source signals, with every 0.1% of squeezed out more mutual information, the more of those components resembled projections of single equivalent dipoles. In other words, which are equivalent to single patches of cortex. That's a beautiful result because, of course, mathematically, you can't predict that at all. It depends on the electrical properties of the signals. And luckily, Jason's Amica is still the most powerful ICA approach for ICA decomposition, which we are fortunate to be able to work with. Okay, I'm going to go faster here. Amica also has a mode in which Chun-Shu recently capitalized on, of looking for periods of stationarity in the data in which the spatial structure of the sources and the source activity structure is more or less the same. And then when the state changes of the subject, then of course you get a different source structure, spatially or activity-wise. And using this, Zenep and I decomposed an hour of a complex video game playing session. If we used one model to model the whole hour, we got equivalent brain sources that could be mapped like this. If we use two models, again, this was a very complex task in which people were doing essentially different things during the task. We found more source signals. We had 3 models, 4 models, 5 models. We could find here 40 brain sources. So this ability to look at non-stationarity and not need to assume stationarity in analysis of EEG is, I think, something that should be exploited in future to a great extent. It's really groundbreaking on the analysis side. Now, here was an early result from, so how do these independent components, are they always independent, totally independent? Well, of course, the brain is connected, so they can't always be. And this was an experiment Julie did in which you could win a penny on every trial and you got feedback. And sometimes the feedback was you won a penny or you lost a penny. But occasionally there would be a da-dum, da-dum, which means on the next trial, if you get this next one right, you win 2 pennies. This produced in these subjects the most widespread explosion of theta activity, a theta burst activity, whose phases were interlocked across most of the brain, as seen by ICA. So this was, of course, this is an advertisement for what? For a casino, obviously. The New Orleans casino. This is what you might call a dopamine moment. So the collapse of the independence in terms of delayed activity, systematic delays in transmission of activity across a network is also what you can see once you decompose the data sufficiently and efficiently. So here is Sean's beautiful result. We had people imagining different emotions. So a few minutes imagining a situation in which you'd feel angry, and then a few minutes in a situation where you'd feel love, and another few minutes where you'd feel anger or grief and contentment and so on. So this is about an hour and a half of unlabeled data. The subject only indicated when they started to feel the emotion and then when they held the imagination of it and then it started to wane and they pressed the button and that would lead to a meditation or a relaxation instruction and then a new suggestion of which emotion to feel. Given the raw data without any labels and time structure whatsoever, ICA found stationary periods of the independent component distribution that corresponded to these single periods, emotion imagination periods. Really quite a stunning result. So we found also recently that, or over these years, whenever we had someone who was willing to do the experiment, that you could decompose other types of biological signals. So electromyogram, EMG. Here was a sleeve we made when we put some of the biosemi EEG electrodes on it. And this was a lab tech at the time. He's now a professor, I believe. Did various actions, and ICA separated out independent muscle signals. Now, those signals have a form that's very surprising to most people who work in ENG. They represent the surface projection of a muscle signal has a polarity reversal at the insertion of the muscle into the tendon at the end of the muscle. It's an end effect. And electrical engineers have predicted that. But here we see it very graphically produced by ICA decomposition of this high-dimensional EMG signal. Currently, Yahya Shirazi in the lab is comparing using a sleeve with multiple channels on it and using a patch applied to the belly of a muscle with very high density grid of electrodes. We're going to do that simultaneously with high density EEG and learn how these signals relate to each other during different motions and movements. Okay, so what about studying EEG in moving subjects? Well, all the brain imaging modalities required people to be still. Why? Because in most of the modalities like MEG or fMRI, the sensors are very, very heavy and you can't walk around with them. But even in EEG, there was also the issue that if you move at all, the signals produced, the artifact signals, the non-brain signals produced by the movement were added into the recorded signals and were thought to be intractable. So it occurred to me that this is very artificial because our brains, again, evolved to organize our behavior in 3D space. Right? Everything from our eye movements, our allocation of attention inwardly, and of course, on the outward, our activities. So could we do it? Because we had ICA, we could. If you want to look at brain and behavior, the relationship, there's the micro activity of the brain, something like a billion gigahertz. That's a quadrillion synaptic molecular events in your brain every second. That's what the brain is doing, and other things. But what we can study, and certainly non-invasively, are things like EEG, ECOG, even spikes or macro phenomena compared to the single synaptic events, which has been the basis of computational neuroscience, actually. But so that out of the extraordinary high dimension micro activity of the brain comes these macroscopic events that occur at various spatial scales, various frequency scales. And then, of course, there's behavior. But the traditional path was to record behavior in EEG experiments only by pressing of a micro switch. You had to call it a micro switch 50 years ago. Every second or so, yes, no, left, right, whatever, to indicate your behavior. So you could now record, a million bits per second easily of EEG, but your recording of behavior was still stuck to 1 bit per second, essentially, on the order of 1 bit per second. And so, of course, that's a huge mismatch. If you want to study the relationship between brain and behavior, what you have to do, well, what people did was just collapse the high dimensional EEG data down to an ERP, and then down to a peak, and then down to a channel, and record one voltage value, and they say, haha, in this circumstance, it's 3 volts, or microvolts, and in another circumstance, it's 5 microvolts. Now let's throw away that data and propose a new experiment. Well, what about the megahertz, a megabit per second of data that you already recorded? The rest of it, why collapse it all down to the level of the behavior? So it occurred to me what you should really do is record more behavior. And then you give yourself a math problem, right? Essentially, what is the relationship between the complexity of your behavior and the complexity of the brain activity that supports it? And so I thought it was so important, this concept, that it should have its own 4-letter acronym like fMRI. And so I said, MoBI, Mobile Brain Body Imaging. With the slogan, record what the brain does, in terms of EEG, for instance, or other things, what the brain experiences in terms of the sensory recording of what the subject experienced. And now my it's covering it, but what does that say, actually? Oh, there it is. And what the brain organizes. And what brain organizes is our behavior. So record that all together. And this was our first task. Klaus Graumann came from Germany and did it. This was given the instruction on the screen to point to different objects, walk over to different objects, and so on. And he was able to use ICA decomposition to find a range of sources. I think this is across a group. And then to look at the spectral perturbations in various source signals in different moments in the experiment, and showed that they behaved exactly as they should. This would be individual scalp muscles that would activate at the time when you moved your head to look at something. And the earlier was parietal activity that would collapse at the appropriate times when you were focusing on something. So, and here's another early study. This was in Gideon Diek's lab. That's a kid and the mom. And they both have some motion capture on their wrists. They both have EEG, and they're playing Pop the Bubble game. The bubbles are appearing on that touch screen, and when they touch the touch screen, it pops. And so that is meant to be a game for the kid. And we had a visitor, a postdoc from China, Yu Lao, who showed, for instance, that one class of components she got from these children was the equivalent of the mu components in adults, although in children it's much lower frequency. It's 8 hertz instead of 10 or 11. And then she showed that the activity, the blue here, the activity collapses not only when the child is going to move and pop the bubble, but when the child observes the mother moving and popping the bubble. And this was the behavior that was much touted at the time, the behavior of mirror neuron cells that in an analogous way change their activity on observing coherent movement. So we were able, very fortunately, to build a MoBI lab downstairs, and we were more fortunate to have a software genius, Christian Kota, come. And when we most needed it, he devised a system for recording from multiple devices at once and synchronizing their signals, the lab streaming layer, or LSL, which now has drivers for over 150 devices, including drivers supplied by many companies that are making those devices, and an active community of open source community of advancing the software. He did many other things, but one of the experiments that we tried using this whole setup that I liked the most was the audio maze experiment, where we constructed a maze in the large MoBI lab that wasn't physical. It existed in the computer model only. And the way you found out there was a wall is you tried to touch it, and then sound would come from the appropriate speaker. Bzz, 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 bzz. So your job was in the dark to explore the maze and come back and then draw what the shape of the maze was after you explore in the dark with the blindfold on. So here was this is a sped up cartoon of the subject touching the walls and exploring the maze. And we had to use simple mazes, we found, because this is a rather hard task. In fact, when we had them come back and then draw from memory the maze, and we see in the colors here the actual trajectory of their walking. And then in the bottom, we saw what they drew when they came back. The first time, they only drew 3 arms, even though they explored 4. The second time, they didn't get far at all. They thought they just went up and down. They forgot they went at least to the right. And then the third time, they performed correctly. So that data are still available. I'm working hard to make it available worldwide in a well-annotated form. I'll come to that. And here was one example of a event-related spectral perturbation at the wall touch moment in a source that could be localized to a lingual gyrus, cuneus lingual gyrus. And when you look up in, for instance, now in Google AI, what is the function of that brain area, of that cortical area? It said it's known to facilitate cross-modal non-visual functions, as well as visual functions, particularly after the loss of visual senses, as in when you're in the dark, which I thought was a very beautiful confirmation that of the fit between what's known about cortical function from fMRI studies now that have accumulated and what is revealed by adequate decomposition of the EEG. Here's another one, the juggling experiment. I challenged our visitor, Hiroyuki Kambra, to record juggling, and here was the setup. Those are 3 balls, and she's juggling them. So here is the structure of the experiment: left, right, throw, catch, throw, catch. And when you time warp the data so you can average it, then you can see for various independent components systematic changes in spectral activity in the alpha theta band here, in the broadband gamma here. And then we discovered something fantastic. Around 75 hertz, a very narrow band. I'm sure if we played this, we could actually hear a hum, because it's so narrow band activity during certain phase of the juggling cycle only. And you see here for other components, we found the same. We thought we could hardly believe it. And then we got a note from a neurosurgeon in UCSF, San Francisco, who said he discovered it in ECOG electrodes, in cortical electrodes in patients, epileptic patients being studied, connected with movements. And he was astounded that we could find it in subjects juggling balls with scalp EEG, with nothing invasive at all. It's there, and the study of ripples is really expanding now. Using MEG, Holgren here has published some fantastic results about it. It's in one of the new, it's perhaps the newest EEG phenomenon, or the most significant or most interesting EEG phenomenon, new EEG phenomenon I've heard of for 30 years or something. So that it's wide open also for study. And here Hiroyuki made a movie. This was his high point of his work. This is for one subject only. And we see on the left the representation of the location of the equivalent dipoles, in other words, the general location of the brain sources that are what I call the effective brain sources that I see isolated from the data. And that should loop, but and so as you see, as she goes through, this is the mean interactions, Granger causal interactions in the alpha and theta bands between these components. And if you again look at the right visual area there, that becomes active. Both it becomes active, and its influence on other areas becomes very active, and only a certain phase of the juggling cycle. And I think just as we analyze what is known about the cuneus in the earlier study, I showed you that result. I think every detail of this picture would fit very well. I have faith that it would fit very well with what's known about cortical function. Only this is interactions on the scale of tens and hundreds of milliseconds, not on the scale of seconds as in fMRI studies. So currently we've been working on 2 projects, the NEMAR project, which now hosts 311 human data sets with almost 30 terabytes of data available from 15,180 participants, increasing by several data sets a week, or a month, certainly several a month. And it's freely available to anyone in the world, the data. But furthermore, analysis of the data on high-performance computing in the supercomputer center upstairs is available freely to anyone in the world. Well, maybe not people from North Korea. Politics do play a little role, but certainly anyone from Taiwan or America or Europe.
North Korea too.
North Korea, no. There is a little bit of vetting that they have to do. They're required to do. So that means you can write MATLAB scripts or Python scripts to analyze any of that data, or potentially all of it, on high performance computing without having to download it and upload it. So this is what I believe is the unit of open science in the future, and that is very large data collections, well annotated, analysis ready, that are intimately and closely physically linked to adequate high performance computing to allow studies using any kind of analysis, of course, including machine learning, that can go across disparate collections of data and not just uniform collections of the data you try to reduce by averaging. So this is the basic unit of open science, it seems to me, and I thought of another acronym for it, the DAT core, the data, tools, and compute resource. And we essentially have it for EEG data by combining the NEMAR data store with the neuroscience gateway to neuroscience, computing for neuroscience. Another invention at the Swartz Center was that of Nima Bigli-Shamlo about a dozen years ago, as he was an engineer, electrical engineering PhD student. And he said, well, how can we compare data sets if we don't know exactly what happened in the different data sets? And it's true, unfortunately, because of historical reasons and maybe intellectual laziness. What is recorded in fMRI studies and EEG studies is just at a certain time, event number 37 occurred. Event type 37 occurred, event number type 56. What is 37? What is 56? It's totally non-standard. In fact, it's often not even reported. Even when people share their data, they just leave that there and they don't explain what 37, 56 mean. So he said, well, there has to be a system for recording in common language that is human readable and machine readable, the detailed nature of events, what the subject experienced or what the subject physically did during the experiment, during neuroimaging time series experiments. No one has thought of this still to this day. There's never been another system proposed. Very fortunate we found a collaborator who is a computer scientist, Kay Robbins of the University of San Antonio, Texas, who has devoted herself to building the software infrastructure for the open source HEAD project, hierarchical event descriptors. And if you go to the headtags.org, you can learn about it. There's lots of documentation. There's AI tools now for annotating your own data, and tools in EEG Lab for using head tags to do analysis of data.
Scott, I meant to ask, how does it relate to neuromorphic event-driven processing?
Neuromorphic event-driven processing.
Once you have those dynamic vision sensors, right, where you have spike events are communicated when something happens in an event, right?
Yeah.
So it's asynchronous. There's no discrete time, and so each event signifies something important to happen in the data. This is related to this one.
So yeah, so the head events are of many types. They can be sensory events, stimulus presented or something happened in the environment. They can be behavioral events, subject to raise their hand, press the button, yawned, had made a saccade, whatever. Or they can be data events, an alpha burst, a beginning of a seizure, whatever alpha burst. And we have a whole language from clinical neurophysiology included in the head now, the SCORE language for clinical reading of EEG. Or they can be mishaps in the experiment, you know, such things that would be in lab notes. Without adequate annotation of events in the data is not analysis ready for anyone. It can't be used. It's essentially a pile of numbers. And no one in the world ever thought of doing it. It's really quite amazing. So it's now available to use. We had to actually create a whole model of what events are and how to fully annotate them. So there's a single timeline for the experiment, no matter how many devices you have. They all want to refer to a single timeline. There are event processes which always unfold through time. They have a beginning and an end, right? That you can call a discrete event process. And our mind works that way. We remember things in terms of events. Well, I went there, then I did that, and then I went there. Those are all events, you see, that unfold under time. I went to the restaurant. I came home. And then there are event markers, what I call event phase markers for the beginning and end of the event, but they can also refer to intermediate phases of the event, like the high point or the low point or the change in the movie that you saw or something. So that these are the basis of HEAD. The experiment timeline, event processes, and event phase markers, condition events, and of course, head tags then refer to all this. And this allows you to do computing on events in context. This event occurred in the context of this condition event, and so on. So I urge you to go to headtags.org and learn about HEAD. Learn about the tools and the exciting AI tools that Young Trung is developing, and Yaya also, and Kay, to make it easy to validate, to learn and then validate head tags. And so this remains the beginning of a whole new era of human electrophysiology, both at the non-invasive level and, of course, as we've seen also on the invasive level, in which all sorts of things are happening. And there's really adequate ground for both basic research, mathematical research, and engineering applications. So have fun doing it. Thanks.
Okay, so let's move on to the last but not the least applications. And the speaker is Professor Chun-Shu Wei from National Yangzhou University. Okay, he is actually our he graduated from UCSD and actually from our lab, from our center, and under Institute for Neurocomputations in 2017. So he came over, I think, 2012. Is that correct? Yeah. So right now he is assistant professor at the Department of Computer Science at NYCU, and he has made significant contributions to signal processing, machine learning, EEG-based brain-computer interfaces. And he and I have co-authors, I think, more than 20 papers, including 8 journal articles in his young career. And Dr. Wei is a recipient of prestigious NCTU Lianghua Junior Chair Professorship. And in 2024, he was honored with the U.S. National Academy of Medicine and Health Longevity Global Grand Challenge Catalyst Award. I think they give 18 awards globally in 2014, and Chun-Shu is one of them. So he is going to present his recent work on deep learning for EEG-based brain-computer interfaces. Let's welcome Chun-Shu.
Thank you, Tim.
Is it working now? Okay, thanks. It's my great honor to be here to share my research, and so especially thanks to TP and also seeing my video.
You should switch on video on your Zoom.
What is that? Sorry, I'm not familiar with Zoom.
No worries.
Oh, okay.
The video.
Oh, okay. When it's not here.
No, that's fine.
Yeah.
The video.
Okay. Oh, my video?
Yes.
Okay.
Good.
Thank you. All right, it's really a great honor, and seeing TP and Gert and Scott, who has been a great mentorship, and also Li-Wei. So today I'm going to share my research about deep learning for EEG-based brain-computer interface. So a little bit introduced for myself. So I started my career in EEG research when I was a freshman in NCTU when I was majoring in EECS. And later on, after I got my master, I came to UCSD pursuing my PhD in bioengineering and working with TP and in a SWOT center. And during my PhD, I spent the summer doing research intern in Mitsubishi Electric Research Laboratory, where I expand my research into deep learning for EEG analysis. So after I did my postdoc in Stanford University, I moved back to now NYCU as an assistant professor and start my own lab in the Department of Computer Science. So this is BCI. I think most people here knows about that. So I've grown up in the era where that lots of scientific movies and animation has BCI element within it. And BCI is basically to translate brain activity into meaningful information for application. So I have a dream is that I can wear BCI, use BCI in my life. So, but I don't want to, get implantation surgery with electrodes. So I would definitely go for non-invasive approach that can monitor my brain activity and consider the cost. Apparently, EEG is one of the best, and it also comes with high portability and temporal resolution, which is very important to develop lightweight, comfortable wearables. So when I got back in NYCU, I started a course brain-computer interface, and it was the first course in Taiwan that comes with a hands-on BCI laboratory activity. So you can see we play drones and also autonomous vehicle in our classroom. So, and you can also see that we're still not very close to getting everyone having BCI in real life, because there are many technical issues to be dealt with. For example, there's a usability, if it's a portable or if it's comfort enough for hours of usage, and if it has good user friendliness, and if its a performance has a good decoding accuracy and robust and efficiency, how it can deal with the very noisy EEG data. And also robustness, how it deals with individual difference and variability and non-stationarity. So we've seen many EEG-based BCI application, and hopefully there's some way to improve the performance and the usability. So today I'm gonna share some of the works that my group has been done recently. So there's one deal with portability and comfort, and also one technique that deal with artifact removal to increase signal quality, and also a new model architecture that increase the robustness of EEG decoding. And also a interesting work that we try to decode image from EEG, and also a tool that we developed for accelerating brain research. So there's an issue with lightweight portable device, and we see that Gert and Li-Wei has shown very important research direction that portable EEG device is very useful. However, when you decrease the size of the device, which means you have limited area to measure the brain activity. So you have limited brain region information from brain regions, and also comes with less number of electrodes. So there's an issue when we try to build a high performance decoding model. So we use knowledge distillation technique, and we designed the first KD framework tailored for EEG decoding. So we first built a high density EEG model that use high density EEG to train a teacher model that comes with good performance. And for the low density EEG, we provide the information from the teacher network during the training of the student network. So the way we did that is to transfer the knowledge from teacher model to student model. So one way is to bring the information from the latent feature within the model to a student model. However, we know that the low density EEG has a different dimension with your high density EEG model. So instead of looking for the similarity between the latent features, we turn into the similarity between the inter-sample similarity within a batch to be used as information for knowledge distillation. And meanwhile, we also keep using the logis loss that works similarly to label softening for regulating the training. So it turns out we validated at 3 different multi-imagery data sets. And here you can see the teacher model has a higher decoding accuracy, and the student model only uses 4 channels of the data and comes with a lower accuracy. And this is how we use KD methods, knowledge distillation methods, to increase the performance. And you can see our method can beat other leading KD methods for all of the data set. So we got a consistent improvement on low density EEG decoding across different architectures and data sets. And another issue is the noise in the EEG data, and Li-Wei just showed their promising work in artifact removal. So in our group, we're also developing a lightweight neural network model based on autoencoder architecture to remove the artifact. So the way we did is similar to Gong Yi's work that we use the reference data collected from the process data of IC label combined with ICA. So this allows us to accumulate lots of reference data for the model to learn. So basically, it's trying to learn how IC label do artifact removal. And we apply, we use multiple subject and multiple sessions of data for our model to learn. And it turns out it can remove the artifact successfully. Here's what you can see for the real-time demo. And since our model is a pre-trained model, so when we apply it in online, it does not require any further calibration. So that makes it a plug-and-play technique for real-time application. And we know that it's hard to tell if the signal quality has been improved from eye observation. So we did a validation using the decoding accuracy on different data sets, and Kling can outperform other methods with the decoding accuracy. So that provides some objective assessment for the signal quality improvement. And this is another work that we developed a new architecture that incorporate Riemannian geometry into a attention neural network. So this allows us to deal with the issue of non-stationarity. As Scott has mentioned, the scalp EEG can be considered as a mixture of the dipole sources activity. So one of the benefit from Riemannian geometry is that we can use that the distance between two representation on the manifold is not affected by the change of transformation. That is the property of concurrence invariance. So you can imagine if we can represent our data by covariance matrices of EEG, then any change in the transformation does not affect the distance between two samples. So you can imagine in one EEG recording session, due to the volume conduction, the mixture might change over time. And with the Riemannian distance, we can allow the processing that's independent with that. So we validate this model on multi-measure data set, SSVP, as well as error-related potential. So this includes both time-locked ERP data and spontaneous oscillatory rhythmic data. So we compare with other leading deep learning methods, and it turns out our model can work quite well on different types of data. This is not very common for other, that can be seen for in other methods. Although we did not got the SOTA for all of them, but I think overall we got a very good result for general EEG decoding. And one of the issues that when we apply these deep learning techniques is that we are we have very limited evidence that the model has been learning about some meaningful information from the data. So there's a need for interpret what the model has learned. So one technique is to use the saliency map that's inspired by the computer vision field. Saliency map is a technique that can provide insight into the model prediction, in which part of the input data the model focus more to get better prediction. And some of the saliency map technique is architecture independent, so which is very useful. You can apply it on a shift. So this is a visualization for the error-related potential. This is what people reported before. That's the prior neuroscientific knowledge. And you can see error-related potential can tell the difference between correct feedback and error feedback to the subject. That's you can see a difference in the ERP waveforms. And here you can see the saliency map of our model. It tracks the difference in the frontal central area as well as the parietal area at quite precise time region. However, there's something here that model probably relies most on this part, which is not sure what that is. So the saliency map, in one hand, echoes the prior knowledge, and on the other hand, it provides some new discovery for us to validate further. So, so let's move to the next work. So decoding image from EEG. So this is a recent work I worked with Chi-Sen, who's in the audience here. So Chi-Sen was a part-time RA in my group. But a few weeks ago, he became a founder of a startup company in Bay Area, which is quite amazing. And I'm glad that he's been able to join us today. So in this work, we are trying to use contrastive learning to help us decoding the image from EEG signals. So the data we use is called Things EEG. It collects the image response of EEG response to the images from 50 subjects that each of them provide 1 hour EEG recording using 64 channel system. And this data set split the training set and test set by having 1,854 object concept. Basically, that's the image classes in the training set, and 200 classes has been left alone as a test set. And the way that did is to have RSVP design, trying to increase the number of images being watched by the subject during a session. So we use the contrastive learning, but we incorporate a thing called inner batch sample similarity. So this is inspired by our previous work of knowledge distillation, that we think that the current contrastive learning does not consider the relationship between the cases. For example, the image of a cat and dog might be more relevant than the image of a cat to a architecture. So we consider the relationship of cases by using the inner batch inter-sample similarity. And then we incorporate this into our contrastive learning. So each of the inner batch similarity is estimated by the cosine similarity between the samples within the same batch. So if you have a 100 sample in the batch, then this will be a 100 by 100 matrix. And similarly, we do the same thing to get the inter-sample EEG similarity within a batch. So we incorporate the loss of similarity keeping into the overall loss, combined with the common contrastive learning loss, that's info NCE. And at the end, we are able to train this framework with different EEG encoder. This is also one contribution we made. We tried different EEG encoder from simple convolutional layer-based architecture to transformer-based architecture. So at the end, we can see the top 1 and top 5 zero-shot image recognition has a better performance given our new architecture using new encoders and also with or without the similarity keeping contrastive learning across most of the subject. So we have done a bunch of work trying to incorporate the deep learning techniques into EEG analysis. And you can see it's very important to have EEG-oriented method design. Meanwhile, we try to leverage the power of AI to accelerate brain research. So what we propose is that since now this model has some feature extraction module that can extract the temporal and spatial information from our data automatically, then it gives a chance for us to leverage this to provide some automated analysis pipeline. And we can build this as a software with a GUI. And so this software can load the data and use the existing deep learning models to decode your EEG data. And through some proper interpretation, you'll be able to see the patterns about the spatial and temporal domains. And if the model can provide nice prediction, then maybe we can develop some new biomarker from EEG. Or otherwise, it also provides a confidence to this pattern to provide some meaningful hints for further mechanism exploration. So we thought that this may be able to, should be able to reduce the human labor and bias during any EEG analysis. So we consider this as a new tool in the field of EEG analysis tools. As you can see, EEG-DAB, we know that it's very powerful. And in this table, you can see why it's so powerful. It provides GUI and also command line interface simultaneously. And it also comes with machine learning based on independent component analysis. So, and there are other tools, but still so far there's no new technique based on deep learning has been developed that comes with both GUI and command line interface, which we thought is very important for cross-disciplinary researchers to leverage our tool. So we developed this tool called XBrainDAB, which is now available in GitHub as an open source tool. So you can see in this panel, you can have information about the data you loaded. And also there's some options for model training. So it uses the core functions of ME Python. So it takes the data for different format. And you can design your, you can assign the classification label from the event markers of your data set. And you can do data set splitting, which is you can design what validation you want to use, how you would like to split into training and test set using this GUI tool. And then you can set up the training configuration for the model training. You can track the training curve to see if it really converge. Otherwise, you might need to change your training parameters. And after that, you can perform, you can inference using your model to give the prediction result with confusion matrix as well as the CASC probability. And at the end, our model interpretation tool can use the saliency map based information to give you scalp information, as well as the 3D projection, as well as the temporal time frequency analysis. So this is an example of applying our tool to motor imagery EEG, where it comes with 4 cases: right hand, foot, tongue, and left hand. So here you can see the activation of contralateral motor cortex in right hand cast and left hand cast. And you can see the other activation with tongue and foot. So we are now releasing this and trying to collect feedback from users. Okay, so overall, we have applied knowledge distillation to increase the performance of low density EEG decoding performance. And we also developed new technical clean to do real-time EEG reconstruction without any calibration. And the manifold attention model provides us robust performance on both evoke and oscillatory EEG decoding. And also we improved the contrastive learning framework to get a sold-out performance for image decoding using EEG. And at the end, we introduced the EEG analytic tool, X-Brain Lab, for accelerating EEG analysis. So thank you very much. I'm open to questions.
Okay, we have time.
What is your tool? What language is your tool written in?
So we're using Python, basically trying to lower the cost as much as possible.
That's pretty good.
It's a general question, right? So when would EEG lab be converted to Python?
All 100,000 lines of code.
Well, there's also chatbots, AI, but
Yes, although the latest I've seen in papers say that programmers find that it takes 15 minutes to write all the code and about many hours to debug the code. So they grumble that I could have written faster. All the debugging is required.
Yeah.
No, Arno's thinking about it.
Okay, let's move to the final session, final discussion. I actually brought some questions from our workshop sponsored by IEEE Brain Society. And I found
So was there a significant difference?
I think the classes, the training classes are independent, so you don't have those classes, the 200 classes in your training set. So that's why it's zero shot problem.
Okay, so they're completely different and there's no similarity.
There may be some similarity.
Is it randomly chosen?
Yeah, for example, there may be also animals or buildings, but there are subcategories. So what you see, the object concept is for those means the subcategories. So there might be some relationship among them because it's largely like animals and buildings.
Mm-hmm.
There are large categories and there are small categories. So so we do, and that's so I think that's also very necessary because there should be some relationship.
Mm-hmm.
Otherwise, it's probably even more difficult.
Mm-hmm. Also, on like the first slide, you explained from the high level EEG to low level EEG, you were using similarity. So, was there any information loss between the number of during the like? I mean, I'm okay with the camera not being to me.
okay.
What you mean the difference between the?
Yeah.
number of electrodes.
No, you said there's a similar, you use cosine similarity, right? You explained the matrix. So was there any information loss when you converted from the high resolution to the low resolution, the second slide, I guess?
You mean the similarity, you mean the KD work or the image work?
The second slide of your presentation, if we can.
The teacher versus student.
Yeah.
Yeah, so, I mean, is there any loss of information when we extract the intersample similarity
Yes.
using cosine similarity? Yes, I think it's just one representation that's available for estimating the similarity between latent features. So we use a cosine similarity that's due to the data probability. We thought that it gives the most it's the most representative distance that we thought at the time. Yeah, but yeah, maybe there are some other ways to improve this to decrease the loss of information.
No, thank you.
Thanks for the
Yeah,
question.
thank you. Yeah.
Thank you. I would invite our speakers to take seats. So we have some discussion. My computer. Oh, you're going to turn it on? Yeah, fine. You can turn it on. Have a seat. Yeah, I got the very, sort of difficult questions when I attended WCCI. Li-Wei was there. Excellent. So I will, based on my memory, I will ask Wei, and then I want your opinions. So first, this basically is related to biosensing. So right now, there's a hot topic using the invasive recording, for instance, Neuralink, and you actually did both the invasive and non-invasive work. And can you actually summarize those pros and cons to this young children?
Sure, yes, of course, and we can match the pedigree of Elon Musk. When he starts something, then he goes to space. SpaceX, he has a revolution in electric cars, and everyone is now eyeing him for a revolution in brain and computer interfaces. But the insiders will tell us that there may be more exciting avenues in the field. Neuralink is definitely great technology, but there's much more to be done. I don't think the main problem is hardware. I think most of the problem is the correct signal processing. Well, a combination of hardware and signal processing and AI, I would say, just good models of what the brain is doing to put it all together. I wouldn't be surprised that advances in AI or the equivalent of large language models will get us closer to getting decoding of brain activity with even lower resolution, non-invasive technologies. Maybe not scaled EEG, maybe something, maybe cortical surface ECOG-like technology would be necessary to give us anything close to truly high resolution, high bandwidth brain-computer interfaces. But who knows? Maybe we'll see what the future tells us. Maybe EEG with good generative AI, good models can actually get closer to. Well, we'll see what happens. But it's not purely about hardware. It's also about the models and the software.
Well, actually, any related questions? That's nice.
And so our last grant application to NIH in DC, in Washington, was to build a foundation model of EEG and event descriptions jointly. And of course, we have the language for event descriptions. That's your unique advantage in HED. And then whatever behavior records, I think in this very large data set, we have eye tracking as well. And with the idea that instead of just building a network to answer one question, like, Sickler, well, or men or women or whatever, we would build a foundational model and then allow users to query the model in many directions or even perform additional training for various purposes. I think that's a promising direction. Now, whether it can read the mind in the sense of the cartoons, remains to be seen. But there's many questions that can be asked of such a model that I think will at least give interesting, important directions for new research.
Mhm. Yeah, well, actually, that's related to my second question. Because let's assume that we can collect tons of data. Then, as you mentioned, Scott mentioned, there's no sort of common architecture or format and to save the data. Why was that? Because nobody thought about that.
Well, I for a chapter, we've written a chapter called Events in Context. For an issue, a special issue of neuroimage on neuroinformatics. And that is associated with storing, annotating, and making available neuroimaging data. And so, yeah, I traced the history of it somewhat. How psychophysiology started with devices that would record a reaction time in around 1850. And something would fall down while the shutter would open and show the picture, and then something would be falling down and stop it with a button press, and then they could calculate the time required. And out of that came eventually the first computer, an EEG computer, which was a man named Manfred Clynes. In 1972 or 71, he created the computer of average transients. It would average epochs, time to some signals, and it would be time to a TTL pulse. And so whatever was controlling the delivery of the stimuli would send a TTL pulse that would say, go. And the stimuli were, and when I started, were generated by analog signal generator. Lambos, my mentor, had dials. You could dial the pitch of the tone and the angle of the attack and all that. And so the TTL pulse would come out the parallel port of the early PC, and it would be an 8-bit parallel port. So you'd have 8 bits, so you'd have an integer value represented in binary by those 8 bits. And so that would be event type 5, event type 37, and so on. So what they would record was that at this time there was event type 5 because of the hardware of the day. But if you go to an fMRI center and find out what these vastly more sophisticated computers are recording, it's usually event type 5 or 37 for it's sort of historical inertia.
There's this parallel to developments in neuromorphic engineering, right? Where we have had a revolution recently, and I mentioned this earlier, right? Dynamic vision sensing, right? So in the old days, you had frame-based vision, still available today, right? You have video, and you send frame after frame, even though nothing changes in the room. Let's say there's nobody moves, it keeps sending the same data over and over again. Vastly done. Of course, the visual system is organized very differently, right? We get unison events when there's something new that happens, either spatially or temporally new, right? And with EEG too, right? So if we have the same waves over and over again, it makes sense to register events when something really happens, and then code that more efficiently, because the Huffman coding out there to the extreme. And so you can imagine maybe the next generation of sensors for EEG could also be event driven, as opposed to just purely just keep sending streams of bits over and over again.
Actually, that reminds me, in the past 10 years, I usually gave a talk about how we can move the laboratory-oriented EEG research to real patients. So at least 5, challenges we're facing. One is we don't have advanced sensor and sensing technologies to simultaneously record not only EEG, but also behavior, contextual information, and also other information, as Scott mentioned, MoBI. So EEG is just one part of solutions, and you already addressed. And Scott mentioned the MoBI and technology. At the time, we actually never thought about the HED. Now you invented this. Yeah. The third problem I see is compared to large language model, we have tons, billions of data sets. But EEG, because it's very costly and labor intensive, so we will never get amount of data like language or like image, like computer vision. How can we go?
Careful, never say never. I mean,
Yeah, yeah.
About the,
They're upstairs, there's 30 terabytes now, for 15,000 subjects and a whole variety of 300
Yeah,
paradigms.
that's why I'm trying to bring up the NEMAR project.
Yeah.
But this is actually related to Leo and Chun-Shu data interpretations. Let's say you have tons of data. If we want to build a teacher model, okay, and do they have to be homogeneous? For instance, the same number of channels, and you have teachers. Some people do 64, some people do 32. You have to throw away 32 channel data, or you're going to throw away 64 channel.
Yeah, that's why I think it should be at the source level. It should be encoded at the source level. Because after all, the skull and the scalp are just producing a linear transform. So does Google, when it does an AI model of images, does it first put them through a broad linear mixing to make the? No, they don't, right? And they wouldn't do that because learning, even if you have a linear layer there, I mean, it takes more data to learn more transforms. So, and linear transforms are not necessarily easier for a nonlinear regression framework. So I think if you start with the actual signal in its natural space, which is the brain, well, perhaps you can, yeah. You can add the eye, the ICA actually extracts eye movements, muscle activities. You can add those too in their own space, but in the native space of the signal, not of the recording device. If fMRI people were analyzing the radio frequency signals coming out of the sensors in the fMRI system, they say, oh, there's a little wiggle on this one, and there's a little wiggle over on this one, so that means they must go together somehow. There would be no field of fMRI. It was because the algorithm allowed them to invert the data and put it back into the native brain space that the whole field was created and the revolution was created. And the same should be for EEG unless there's severe constraints on number of channels and so on. Although I doubt that those economic constraints are going to be long lasting.
I agree with Scott saying scalp imaging is not brain imaging. Yeah, so actually I feel there's a chance for us to go into the brain architecture using the common human brain across different subjects. The heterogeneous part is the device that we record, but they're recording the projections. So we should get into the source and use as much power as possible to know to understand the brain dynamics. And I feel what we see from a language model is that even though it's not some general AI, but it's already able to memorizing a lot of things. So maybe it's there's a chance to construct the brain dynamics within the parameters, as it has so much parameters.
One slide I didn't get time to put in today was the fact that the biggest problem in localizing sources in EEG. What is the biggest unknown variable? It's the skull conductance or skull resistance. He's a hard-headed guy, see. I'm soft-headed, but no, it's true that in adults, our calculations are that there's a 3-to-1 difference in resistivity of the brain overall, of the skull overall. And of course, in kids and babies, it's much different as well. And that makes a huge difference. Zeynep made a nice paper on modeling it. And it makes a huge difference in the implied location of sources in the brain. And if you're really interested in the brain and exactly what part of the cortex and what part of the cortical fissures the source is in, then it makes a huge difference. And so we invented an algorithm that to actually treat the ICs as effective electrodes, as stimulating electrodes. And simultaneously localize all of them to the cortical surface and find the skull resistivity that maximizes the fit of the solution. And it's a very stable solution over days or weeks or months. You'll find the same value for the same subjects, while different subjects has very different values. And that can make a big difference in the accuracy of the localization. So it's not something that people really have picked up, and Zeynep retired, unfortunately, before it was ready to be used by other people. But yeah, is trying to make that possible. And we'd like to, because it's computationally intense, we'd like to put it on the neuroscience gateway so people can use it in an efficient way. And that, yeah, it's quite interesting. The primary obstacle is how hard-headed the subject is.
Okay.
Yeah. So can we, I mean, could be a naive question and probably a naive way, but can we do that by detecting the difference between invasive ways of sensors and non-invasive sensors?
Well, yes, that would be possible if you want to stick something in there. Essentially, we use the ICs as if they were virtual implanted electrodes. You can also use simultaneous EEG and MEG because, of course, the skull affects them quite differently. But that means you have to have a $2 million shielded room.
But it will be simpler, right? Because we may get we may have some ground truth, right? There's always going to be we know that certain signals always originate from the same location in the brain.
Yeah.
And so whether you have a hard head or a soft head, right? You can still
but the
calibrate based on, right?
But you can't count on the amplitude being the same for different subjects.
So if there's enough data, it's not sufficient to fill in the fit of parameter, that softness, hardness parameter. If it's 1 or 2 parameters in model, then you have tons of data.
I would doubt it. I mean, to say that the distribution of alpha activity, for instance, the power of the alpha, the distribution of it, even over a long time, is going to be the same for you and for me. I would doubt it. Yeah, the more you know someone else, the more you know they're different than you.
Well,
And those of you who are married know that very well.
actually, one of the problems in data analysis is intro and inter-subject variabilities.
Yeah.
The other questions I raised, I mentioned in my talk is about the label data. A lot of, actually, we have limited number of data, for one. And unfortunately, the correctly labeled data are sparse. Oftentimes, we got mislabeled data. And that's particularly for BCI. For instance, you want to do emotion detections. And you look at one video, or listen to a video for 1 minute, and you have one label, like valence arousal. But you assign this label to every single second of this recording. That's wrong.
Yeah.
Okay. So do you think that's with this soft labeling or different?
Yeah, so actually, we've done a work showing there's a variation in the emotion intensity during a emotional video watching. So that's definitely, existing. So and label softening has been shown very beneficial for EEG decoding. So I think there are ways to deal with that based on the uncertainty of prediction of your model. But still, I think lack of ground truth is one big issue.
And you, I think, face the same challenges. For instance, the sleep stages. And if you get two physicians score the sleep stages, and they got like 85% agreement, and so your labels only up to 85%. So how do you deal with that?
Yeah, yeah. In clinical study recently, we found that an interesting thing is that we can use unsupervised learning method to quantify the data first. So then you can use the supervised data to refine to the label of the data.
Yeah, that's the same issues with the software labeling.
Yes, yes. So very interesting that, but I didn't show today, because recently we got a published paper, human somatosensory sensitivity. So that can be, categorized, to different categories. Yeah, for instance, in Taiwan, Taipei Veterinary General Hospital, we performed the experiment that the subject to perform 4 different stimulus, like a temperature stimulation, like a hot and a cold stimulus, and also mechanical stimulus, like a pressure and the stimulus. Yeah, so in the beginning, subject, they just evaluate their personal behavior. But after that, we want to understand the sensory type or how sensitivity from the potential migrant patients. Yeah, so then we do unsupervised learning, to try to separate that. So interesting that we can divide them, these patients, these potential patients, to 4 different subtypes, like all sensitive and the non-sensitive, and the temperature sensitive, and also mechanical sensitive. So very interesting that they are balanced and labeled that. So after that, we use the supervised learning to test that. So they are quite consistent, and can just adjust some label, relabel
That's related to the subject variability. Scott must remember, when you publish the papers in PNS, we actually separated fast responder versus slow responder. Their ERPs or single tracks differ.
Well, one study I didn't talk about was the emotion study with Julie, where we had people imagine the emotion. And then there was so much in that data that's still there, and it's have we fully labeled it with head yet? Make it available? I hope so, but we need to. There's so much information in there, but we pulled out one thing that we finally got published, that how good or bad was the emotion. So we didn't have the subjects themselves say how good and bad the emotion was. We just looked at the dynamic state of the system, and projected the 15 dimensions of the 15 emotions down to a 2-dimensional space. And then we saw a 1-dimensional structure in it. And so we took the terms, love, hate, fear, anger, and we asked a group online, how positive is this word? How negative is this word? And they used a slider, I think. And so they, that love is more positive than hate, right? Or, whatever. Then we looked at the weights on that 1-dimensional scale, and we related it to the EEG, 15 dimensions reduced to 2, and the fit was R.96.8. In other words, you can tell from the EEG exactly how positive or negative the feeling is. That's what it says, that the person is experiencing. And I mean, extraordinarily high correlation, and that's with knowing nothing, the EEG analysis, knowing nothing about emotions or time periods in which they were doing this or that. And that was, it turned out to be, well, I'm sure there's more information, but we were studying the high frequency broadband activity. You might call it gamma, but it really went up to as high as 250 hertz, starting at about 30. We looked spatially where those sources were across all 30 subjects. And there were 2 spots in the temporal cortex. And the amount of high frequency activity there, which should correspond to something like spike rate, could tell very precisely. And apparently within a few seconds of recording, how positive or negative the feeling was.
It's probably more than positive and negative, right? That would be one dimension.
No, that was the first salient dimension that we pulled out.
Yeah.
So there's much more information in there, definitely.
Excited versus calm. There's also orthogonal, right?
Yes,
Other bands,
that's right, that's right. And we didn't get to do that. We didn't look at the other frequency bands. We decomposed the spectrum into different independent bands, and there was just too much to do, and getting anything published was hard because it was all new. In fact, the reviewer, and we finally went to one journal, and the reviewer said, you can't publish a new task paradigm, and a new analysis method in the same paper. And I wrote back, that's why we went to a journal called Frontiers in Neuroscience. They couldn't say anything.
Okay, I have 2 questions. Then we can have to end the session. Otherwise, we could go for another 10 hours. One is specifically for BCI. And this is $1 million questions. If we focus on non-invasive EEG, what are the most sensible applications in BCI? That would be you too. And another related question is, Gert, in-ear EEG, would that help to move these real world applications, BCIs, forward?
Yeah, from my point of view, that's the reason why I show today, in smart healthcare applications, because I in the past 10 to 20 years, work on this study. So my PhD study started driving EEG analysis. Scott, you know that well. With Professor C.T. Lin. So I found that no matter what I develop a new algorithm or with a sensor, so I can ask a question to everyone. You can drive, you are a driver, but will you want to use, no matter an EEG, how small it, so before you driving, you need to put it on your head so that can detect your drowsiness level, and so that work, and do you want to use that? So I asked many people, no one want to use that.
Well, now in-ear, earbud, EEG,
So,
that's a possibility,
yes.
particularly young generation. I saw them wear earbud all the time. I don't know if they are just listening to music or they are trying to avoid conversation.
It's a fashion symbol, right?
Yeah.
Either you're young or you're old, right? So it's young, and then you're a teenager and you want to be cool. If you're old, you have to wear hearing aids, right? Or either way. But I think in terms of future directions in EEG or PCI, we can be very bold in thinking, given all the revolution that we have seen in deep learning and AI. It's amazing what is available today. I mean, 20 years ago, if anyone would mention that you can have an intelligent conversation with a computer, right? That would have been laughed at, right? But so it's not impossible for us to conceive that 20 years from now, that we may have truly intelligent BCI systems, invasive or non-invasive. We can probably, what is called invasive today may well be very unobtrusive in the future, but still be something that you can, that can be in your bloodstream or whatever, right? It's not impossible. We'll see what happens in 20 years from now or 30 years from now.
I got those questions all the time. what will be the most sensible or low-hanging fruit for companies.
Today we're all, I guess, well, now 30 years ago, our children would go play and play hard, right? Today you go to a playground and they're all with their thumbs.
Or even, on the dining table. It's not
Yes,
talking to
yes.
anybody.
So that changed. So that's, I guess, for worse. That's done. But you can imagine the same linear projection moving forward. It may well be possible that throw away all those devices. What you need is this device with a, right? If you can actually communicate directly with others without having a device, right? Without using your thumbs, that may be a future possibility, right?
But I think on the practical side, didn't you have the experience in China where they asked the big room of Chinese BCI scientists what practical applications exist? And the speakers pointed to Ziping in the audience, right?
Well, actually, these 5 of them in 5 different areas: clinical applications, cognitive and affective states assessment. Yeah.
But in the clinical applications, Ziping found a very good one, I think.
Yeah.
I don't know what it's the status of that is now, but it would be interesting to hear what is the status
Well,
of
we
that
move on
project.
to actually other things. We file patent and also publish paper to move that to, for instance, multiple sclerosis, and basically trying to detect both the efferent and afferent visual dysfunctions, and that could be applied to dementia detections and also TBI and others. So yeah.
But about the original testing of glaucoma?
We still move on, but now we don't really have manpower to analyze data. We collect data from 300 eyes and at Duke University, based from the fundings by NIH. We're still mining data.
Yeah, because I mean, you can make quick, non-invasive tests that are much more advanced than the clunky ones that medicine still uses for many applications. They took us to the ophthalmologist took us to his lab or his clinic. And he said, this is how we test for glaucoma. Glaucoma creates blind spots, right, where the retina. And he put us in this Flash Gordon sort of, I don't know if you know Flash Gordon, but he was a 1930s sci-fi space explorer on American television and comic books. And there's an ancient device, and it made little lights, but it made a sound every time it made a light. So all you had to do is push a button whenever you heard the sound, and it would say you have perfect vision. Even if you were blind, you could. It was like so stupid. It was so inaccurate. And so Ziping went home and thought, haha, this is where we could make a device. And yeah, and it has I think still a great potential. So that's certainly one area in which I mean it's fun to think about, communicating with our brainwaves and so on, but places where knowledge of brain activity is really crucial for making diagnoses.
So
it's a good
what about
opportunity.
basically you think that the health related applications will be number 1. And how about Chun-Shu? What do you think?
Yeah, totally agree. I don't have good judgment on that, but my proposal reviewers has told me that healthcare is a way to get grant.
Well, last questions. We're talking about BCI, that's applied research. And how about fundamental brain research? With new technology, with new sort of HED common format, what do you think that we should go next? For instance, pretty much, I hope I do not offend anyone. In the past, I would say 90 years, people are still focusing on stimulus response contingency. So it's a very simple-minded experiment. And Scott mentioned, MoBI mentioned, I would say the brain at work. No, in the wild, we call data. And what do you think? What the brain research, not only EEG, should Well,
Well, I mentioned a couple of things I thought, non-stationarity. I mean, the fact is we can react to, I react to what he says, I react to you looking at me and trying to see if you're understanding me or not. So things are always changing and our brain pattern has to change. So looking at that, I think is, and finding methods to analyze that is very important. The structure, in terms of EEG, of course, we want to look at the sources, and so the head modeling is very important. In terms of movement, the roboticists have their, clunky robots, and so they look at joint torques because they have a little motor in there, and they'll have to turn on the motor to what extent. But Hirokazu, Tanaka, and Perry have written papers saying that the basic representation of body position and body movements shouldn't be based on joint torques. And it's very unlikely that the brain is interested in joint torques. It's not saying elbow move to 32 degrees and pick up, There's a much more natural system based on perception of distances between pairs of joints. I know how far my hand is from my, let's say, the center of the body here. And I regulate that when I pick up something, rather than I'm going to move my elbow at this. And he showed mathematically that you could represent movement and forces, body forces, perfectly in that system. So for MoBI, it seems to me, for instance, that that's the system you should capture motion capture in, and then brain activity in the suitable form, and then apply AI. So I think it does sort of fundamental levels of non-stationarity and proper putting the data into the proper representation will be really important for progress. Unfortunately, there's very few people who combine that sort of level of interest in the math, and sensitivity to what is more natural maybe more natural for the brain. So I'm still looking for people who work on that.
Okay, I will give the last opportunity to the audience.
I'm just wondering, if any possible to do a trial-free or event-free EEG signal, because I think we typically we just think anything anytime. We are rest most of the time, and we have some wondering, oh, I have one thing to do, or I will try to do that. So now EEG experiment is for trial-based and event-based. We need to think a lot, 20, 60, 100 times, but this is not real world working. Yeah, and every EEG open data set is based on trial. And one of the most important key, I think, is I cannot visually or audibly to know what is signal for. So we need to write down what is this open data set what to do. So and another maybe channel number or another. So we cannot do the data to the general. Yes. So yeah, my question is there any possible to do trial-free or event-free? Yeah.
Well, the rest paradigm, resting fMRI, was invented by Marcus Raichle, who used in the beginning of fMRI, they would have people do the task for a minute and then rest for a minute and do the task. And they wanted to find out what was, they thought the brain would be active during the task and doing nothing during the rest. But of course, they found out the brain was doing other things during the rest. And that was the beginning of the whole move toward resting fMRI. Now, fMRI is such a slow signal that event-related analysis is not very efficient. The events would be do this for a minute and stop. So there's been a whole revolution in rest. But what Marcus Raichle told me, you know what rest stands for? randomly excited silent thinking. And so now there's beginning to be a backlash, even in fMRI, against this simple assumption that the brain is doing nothing or the brain is doing one thing. So I mentioned non-stationarity as a very important, if you can find stationary periods in the EEG to make a model of, and then see how those models change, that would be very useful. Another algorithm I worked on with Julie was context ICA. Even if you have a trial-based task, the way your brain approaches the problem of this trial depends very much on what you just experienced in the last trial. Just like in a gambling casino, people, if it comes up heads 5 times in a row, they'll put all their money on tails. The gamblers fallacy.
Even though it's absolutely.
Even though there's no, because we can't override that ability to, or that the brain relies on prediction. We want to use what's just happened to predict what's just about to happen, because that will help us make the appropriate response. And even if you have the simplest trial-based task, every trial that you find that the brain activity in that trial varies in subtle ways depending on what's been in the previous trials, and particularly the value of what's been. So even in trial-based analysis, the idea that the brain just gives a rigid linear response is wrong.
Mhm.
And so we found a method for actually probing that and finding these slight differences that were hidden under the ERP or the ERSP that could tell you whether you were going to get it right, the trial right or wrong, and so on. So yes, the non-stationarity, and when I say events, it doesn't have to be events in a trial-based experiment. You can also have events in a movie. So what are the events in a movie? Oh, that's a difficult subject, right? But we're working at it.
Extending the rest modalities. So we spend actually 1/3 of our lives through rest, I guess, during sleep. And we can do sleep staging, so you saw today, right? You can do all this and analyze sleep quality. But more than that, I wouldn't be totally surprised if maybe 20, 30 years ago, we can actually record our dreams and find what we have been dreaming in them.
Okay, well, 37 behind schedule. Yeah, really appreciate our speakers, and let's thank them again. Stimulating discussions.
And I appreciate our host, Ping, also.
And yet, it's so wonderful to have this collaboration, right, between the INC, the Schwartz Center, and Taiwan, right? And Chipping, you have definitely orchestrated this two-way channel, right, of Taiwan. That's been wonderful and very productive. In fact, if you see the world of EEG today and BCI today, it's really those two poles, right, which we have great progress that has been made over the years. So let's continue. It's great.
Okay, thank you.
Yeah, so let's take a group photo together.
Okay.
Take this opportunity. What do you think? Yeah.
Because it's,
Here or on the steps?
yeah, you four have you sit here, and we will take photo.
Yeah, maybe Zendra, hey.
Oh.
Zendra is still in the office.
Yes.
Actually, if we could have any questions from the audience.
I checked, and not really, no. Except some technical questions I will
I see,
answer,
I see.
and that's my student who will answer.